Stars are everything. Every atom of oxygen you're breathing right now was forged inside a star. Every atom of iron in your blood, every atom of calcium in your bones, every atom of carbon in every molecule of every living thing on Earth. All of it came from stars. You are, in a very real and non-metaphorical sense, made of star stuff. That's not just a nice thing Carl Sagan said. That's chemistry. That's physics. That's the literal history of the atoms in your body. And there are a lot of stars, more than you can really conceive of. The observable universe contains something like 2 trillion galaxies, and each galaxy contains, on average, maybe 100 billion stars. Multiply those numbers together, and you get something like 200 sextillion stars. 2 followed by 23 zeros. That's more stars than there are grains of sand on all the beaches of Earth. By a lot. Some estimates say there are 10 times more stars in the observable universe than there are grains of sand on Earth. Others say 100 times more. The exact number doesn't really matter because at this scale, the numbers stop being meaningful in any human sense. There are just a lot, and every single one of those stars is doing something. Burning, fusing, radiating, living out its life on timescales that dwarf human civilization. Some of them are just being born, coalescing out of clouds of gas and dust. Some are in the middle of long, stable adulthoods, quietly turning hydrogen into helium. Some are in dramatic old age, swelling up into red giants and casting off their outer layers. Some are in the process of dying, collapsing into white dwarfs or neutron stars, or occasionally black holes. All of this is happening right now, everywhere in the universe, all at once. So when I say I want to talk about the types of stars, what I really mean is I want to talk about all the different ways a ball of gas can be interesting when you make it big enough. Because that's what stars are fundamentally. Balls of gas. Very big, very hot balls of gas. And depending on how big they are and what they're made of and how old they are and what's going on around them, they can be radically different from each other. So different that calling them all stars almost feels like a category error, like calling a hummingbird and an ostrich both birds. Yes, technically, but the differences are enormous. Let me start with the basics. What is a star? A star is a ball of gas, mostly hydrogen and helium, that is held together by its own gravity and is hot enough at its center to fuse hydrogen into helium. That's the standard definition. Gas, gravity, fusion. Those are the 3 ingredients that make a star a star. The fusion part is important because without fusion, you don't have a star. You just have a ball of gas. And the universe has plenty of balls of gas that never quite become stars. Jupiter, for instance, is a ball of hydrogen and helium held together by its own gravity, but it's not hot enough at its center to fuse hydrogen, so it's not a star. It's a planet. There's a threshold, a minimum mass below which fusion can't happen, and that threshold is one of the most important numbers in astrophysics. The threshold is about 8% of the mass of our sun, or, put another way, about 80 times the mass of Jupiter. If you have a ball of gas smaller than that, you don't have enough gravitational squeeze at the center to compress the hydrogen to fusion temperatures. So it just sits there, being warm and gassy, but not a star. Between planets and stars, there's a middle category called brown dwarfs. These are balls of gas bigger than Jupiter, but smaller than the hydrogen fusion threshold. They can fuse deuterium, which is a heavier isotope of hydrogen, for a while when they're young. And the biggest brown dwarfs can fuse lithium, but they can't sustain hydrogen fusion. So they're kind of failed stars, objects that almost made it, but not quite. We'll come back to brown dwarfs in more detail later. Above the fusion threshold, though, you have stars, real, actual fusion-powered stars. And within that category, there's a huge range, from tiny red dwarfs that barely make the cut to enormous blue supergiants that are millions of times more luminous than our sun. And between those extremes, every possible variation in size, temperature, composition, and behavior. To make sense of all this variety, astronomers use a classification system. Actually, several classification systems. But the most fundamental one is called the spectral classification. It sorts stars by their temperature based on the light they emit. The spectral classification uses a series of letters: O, B, A, F, G, K, M, from hottest to coolest. The traditional mnemonic for remembering this order is, "Oh, be a fine girl, kiss me," which is charmingly dated and slightly weird if you say it out loud in the modern era. Some people have proposed alternatives like, "Oh, be a fine guy or girl, kiss me," to modernize it. But whatever, O, B, A, F, G, K, M. That's the order. O stars are the hottest. Their surface temperatures can exceed 30,000 degrees Celsius. They're blue, almost blue-white, and they blaze with tremendous intensity. B stars are next. Still very hot, maybe 10,000 to 30,000 degrees at the surface, and still blue-white. A stars are white with temperatures around 7,500 to 10,000 degrees. F stars are yellow-white, around 6,000 to 7,500 degrees. G stars are yellow, around 5,000 to 6,000 degrees. Our sun is a G star. K stars are orange, around 3,500 to 5,000 degrees. And M stars are red, below 3,500 degrees. Each of these letter categories is further subdivided by numbers, from 0 to 9, with 0 being the hottest end of the category and 9 being the coolest. So our sun, for instance, is a G2 star. It's near the hot end of the G category, but not right at the boundary with F. If you want to get even more specific, there are additional letters called luminosity classes, which tell you not just the temperature, but the size and brightness of the star. Roman numerals from 1 to 5, with 1 being the largest and most luminous supergiants, and V being the main sequence stars, which are the normal stars in their prime of life. Our sun is a G2V star. G2 for its temperature, V for its luminosity class, meaning it's a main sequence dwarf. Now, hearing our sun called a dwarf might be surprising. The sun is huge, right? It's over 100 times the diameter of Earth. It contains more than 99% of the mass of the solar system. Calling it a dwarf feels wrong. But in the context of stellar classification, dwarf just means a star on the main sequence, as opposed to a giant or supergiant, which are much bigger. Compared to those, the sun really is small. A perfectly average, unremarkable, run-of-the-mill dwarf star. Nothing special about it from the perspective of the galaxy at large. Okay, now that we have the basic classification system, let me start walking through the actual types of stars. I'm going to organize this by starting with the smallest, coolest, most common stars and working my way up to the biggest, hottest, rarest ones. Because that's roughly the order of their abundance in the universe, from most numerous to least. Let's start with M dwarfs, also called red dwarfs. Red dwarfs are the most common type of star in the universe. Depending on how you count, they make up somewhere between 70 and 80% of all stars in our galaxy, which is astonishing. When you look up at the night sky, you don't see many red dwarfs. In fact, you can't see any of them without a telescope. Every single star that's visible to the naked eye is more massive and brighter than a red dwarf. But that's because red dwarfs are so dim, they don't shine brightly enough to be seen from any significant distance. If you could somehow see all the stars in the galaxy at once, regardless of distance, red dwarfs would dominate the view. They're everywhere, but they're quiet, faint, easy to overlook. A red dwarf is a star with a mass somewhere between about 8% and 60% of the sun's mass. They're small, they're cool, with surface temperatures between about 2,300 and 3,900 degrees Celsius. They're red or reddish-orange in color, and they're extremely dim. The smallest red dwarfs emit less than 1/10,000th of the sun's light output. Some of the very smallest emit less than 100,000th. They're barely burning at all, but here's the amazing thing about red dwarfs. Because they burn so slowly, they last forever, or close enough to forever that it doesn't matter. A red dwarf with, say, 20% of the sun's mass has a projected main sequence lifetime of something like 1,000,000,000,000 years. That's 1,000 billion years. The universe itself is only about 13.8 billion years old, which means every red dwarf that has ever formed is still, in a sense, young. None of them have died yet, not a single one. The universe is not old enough for even the oldest red dwarfs to have finished their main sequence lives. Think about what that means. The universe, as we currently observe it, all 13.8 billion years of it, all the galaxies and quasars and gamma ray bursts and everything else, is just the opening moments in the life of a red dwarf. Trillions of years from now, when every other kind of star has burned out and died, when the last blue supergiants and yellow dwarfs and orange giants have all faded into the dark, red dwarfs will still be burning. They'll be the last stars. The universe will end its era of light with a whimper, not a bang, as the final red dwarfs slowly cool and fade over the course of unimaginable amounts of time. There's a whole area of speculative astrophysics called the far future, or the deep future, which tries to predict what the universe will look like at these enormous timescales. And red dwarfs figure prominently in those predictions, because they're the last stars, the final light in the darkness. When the universe is 1,000,000,000,000 years old, 10 trillion years old, 100 trillion years old, red dwarfs will still be the dominant type of star. Everything else will be long gone. Now, red dwarfs also happen to be really important for the search for life beyond Earth. Because if you're looking for habitable planets around other stars, and if you want to find them in large numbers, red dwarfs are your best bet. There are more of them than any other kind of star, and they last long enough for planets around them to have plenty of time to evolve life. Compared to a sun-like star, which will only be stable for maybe 10 billion years, a red dwarf gives you 1,000,000,000,000 years or more. That's a lot of runway for biology to do its thing. But there are complications. Red dwarfs are dim, which means the habitable zone around them, the region where liquid water could exist on a planet's surface, is very close to the star. And when you're that close to a star, you get tidally locked, meaning the planet's rotation slows down until one side always faces the star and the other side always faces away, which creates all kinds of interesting problems for climate and habitability. The day side would be intensely heated. The night side would be frozen. There might be a habitable ring around the terminator, the boundary between day and night. But it's a much stranger setup than what we're used to on Earth. Red dwarfs are also um, temperamental. Many of them are quite active. They have strong magnetic fields, and they produce frequent, powerful flares. A red dwarf flare can be many times more energetic than a solar flare from our sun. And because habitable planets around red dwarfs are so close to their star, they get blasted by these flares much more intensely than Earth gets blasted by solar flares, which could strip away their atmospheres, sterilize their surfaces, or otherwise make them uninhabitable, despite being in the technical habitable zone. The star Proxima Centauri, which is the closest star to our sun, is a red dwarf. It's an M5.5 star, meaning it's near the cool end of the M category. It has about 12% of the sun's mass. And it has a planet in its habitable zone called Proxima Centauri b, discovered in 2016. Proxima b is roughly Earth-sized, and it orbits the star every 11.2 days, which is a very short year because it's very close to the star. Whether Proxima b is actually habitable is one of the big open questions in exoplanet science. It's tidally locked. It gets blasted by frequent flares. But it has liquid water potential in principle. So we don't know. Another famous red dwarf is TRAPPIST-1, which is about 40 light years away and has 7 known planets, several of them in the habitable zone. TRAPPIST-1 is an even smaller and cooler red dwarf than Proxima Centauri, an M8 star with only about 9% of the sun's mass. It's just barely a star. If it were any smaller, it would be a brown dwarf. But it's a star, and it has this remarkable planetary system, and it's one of the most heavily studied stellar systems in modern astronomy. The James Webb Space Telescope has been observing the TRAPPIST-1 planets to try to characterize their atmospheres, and the results so far have been mixed. Some of the planets appear to have no significant atmosphere. Others are still being studied. It's early days. Barnard's star is another notable red dwarf. It's the second closest star system to us, after the Alpha Centauri system, at about 6 light years away. It's famous in astronomy for being the star with the largest known proper motion, meaning it moves across the sky faster than any other star. From our perspective, it's a very old red dwarf, possibly 10 billion years old or more, and it's moving quickly relative to the Sun because it's on a different orbit around the galactic center. Barnard's star was long speculated to have planets, and various proposed detections were made and then retracted over the years. As of relatively recently, there's evidence for at least one planet around Barnard's star, but the details are still being worked out. Okay, red dwarfs. They're small, they're common, they're long-lived, they're dim, they might have habitable planets, they might not. That's the basic story. Let me move on to the next category. Above red dwarfs, we have K-dwarfs, also called orange dwarfs, though the name is used less commonly. These are stars with masses between about 60 and 90% of the sun's mass. They're slightly cooler than the sun, with surface temperatures between about 3,900 and 5,300 degrees Celsius. They're orange in color, though the difference between an orange dwarf and a yellow dwarf like the sun is subtle to the eye. K-dwarfs are interesting because some astrobiologists have argued that they might actually be the best type of star for habitability. Better than red dwarfs, better than sun-like stars. Here's the logic. K-dwarfs are cool enough that their habitable zones aren't too far from the star, so planets there can be common, but they're warm enough that the habitable zone isn't so close that planets get tidally locked or blasted by flares. K-dwarfs also last a long time, maybe 20 to 70 billion years on the main sequence, which is much longer than the sun. That gives plenty of time for complex life to evolve. And K-dwarfs are relatively quiet magnetically. They don't produce as many flares as red dwarfs, so planets around them get a more stable, gentle environment. For all these reasons, some researchers have suggested that if we're really serious about finding advanced extraterrestrial life, we should focus our search on K-dwarf systems. There's even a term for this idea, the Goldilocks stars hypothesis. K-dwarfs are just right. Not too hot, not too cold, not too short-lived, not too active. The perfect balance for long-term habitability. Epsilon Eridani is a well-known K-dwarf, about 10 light years away. It's a young star, only maybe 400 to 800 million years old, so it's still magnetically active. But it's often mentioned in discussions of nearby stars that could potentially host life. It has at least one confirmed planet, a gas giant, and there's evidence for others. 61 Cygni is another famous K-dwarf system, or rather two K-dwarfs orbiting each other. It's about 11 light years away, and it was the first star system other than the Sun to have its distance measured back in 1838 by the astronomer Friedrich Bessel, which was a huge moment in astronomy. Before Bessel, we didn't really know how far away stars were. We had guesses, but no measurements. Bessel used the technique of stellar parallax, which involves measuring the tiny shift in a star's position as Earth orbits the Sun and calculating the distance from the geometry. He got a distance to 61 Cygni of about 10.4 light years, which is very close to the modern value. That measurement changed astronomy forever. It showed that we could actually measure the distances to stars and therefore start to build a real map of the galaxy. Alpha Centauri b is a K-dwarf too. It's part of the Alpha Centauri triple star system, which is the closest star system to us. Alpha Centauri a is a G-star, similar to the Sun. Alpha Centauri b is a K-dwarf, slightly smaller and cooler than the Sun. And Proxima Centauri, as I mentioned before, is a red dwarf in a very wide orbit around the AB pair. So Alpha Centauri has all three of the main habitable zone star types in one system, which is convenient if we ever want to send an interstellar probe. Whichever type of star turns out to be best for finding habitable worlds, we can check off all three by visiting Alpha Centauri. Speaking of Alpha Centauri, there's an interesting project called Breakthrough Starshot, which is a proposal to send tiny gram-scale spacecraft to Alpha Centauri, using powerful lasers to accelerate them to about 20% of the speed of light. If it works, the probes could reach Alpha Centauri in about 20 years, which is fast enough that people alive today could see the results, in principle. Whether the technology will actually work is an open question, but the physics is at least plausible. And the target is Alpha Centauri, because it's the closest system and because it has this interesting mix of stellar types. Okay, K-dwarfs, slightly cooler than the Sun, potentially ideal for habitability, long-lived and stable. Let's move up the mass scale to G-dwarfs. G-dwarfs are stars like our Sun, yellow main sequence with masses between about 80% and 105% of the Sun's mass. Surface temperatures between about 5,300 and 6,000 degrees Celsius. They're the type of star we know best, obviously, because we're orbiting one, and they're often called sun-like stars, or solar analogs, or sometimes yellow dwarfs. The Sun itself is a G2 star, as I mentioned. It's a middle-aged main sequence star, about 4.6 billion years old, and it has about 5 billion more years of main sequence life before things start to change dramatically. During its main sequence life, the Sun is basically stable. it gets slightly brighter over time, which is a normal part of stellar aging, but the changes are slow enough that they don't affect us on human timescales. G dwarfs make up only about 7 or 8% of all stars in the galaxy, which is surprisingly few, given how central our star feels to us. There are roughly 10 times more red dwarfs than G dwarfs. But because G dwarfs are much brighter than red dwarfs, they're overrepresented in our view of the night sky. Many of the familiar bright stars are actually not G dwarfs. Most of the really bright stars are giants or supergiants or hotter main sequence stars. But some familiar stars are G dwarfs. Alpha Centauri A, as I said, is a G2 star, essentially a twin of our Sun. It's slightly larger and slightly brighter, but only by a few percent. If you could magically transplant Earth to orbit Alpha Centauri A at the right distance, we probably wouldn't notice much difference in our daily lives. The star would look almost identical to our Sun. Tau Ceti is another famous G-dwarf, about 12 light-years away. It's a G8 star, so it's near the cool end of the G category, closer to being a K-dwarf. It's slightly smaller and dimmer than the Sun. Tau Ceti is one of the closest Sun-like stars, and it's been a target of interest for astrobiologists for decades. There have been various claimed detections of planets around Tau Ceti, though the situation is complicated because the star has a large debris disk that makes signal analysis difficult. 51 Pegasi is a G-star that's famous for a specific historical reason. In 1995, 51 Pegasi became the first Sun-like star found to have a planet. The planet 51 Pegasi b was a hot Jupiter, a gas giant orbiting very close to its star, completing an orbit in only 4.2 days. This discovery by Michel Mayor and Didier Queloz kicked off the entire modern era of exoplanet science. Before 51 Pegasi b, we knew of a few planets around pulsars, but no planets around normal Sun-like stars. After 51 Pegasi b, we knew that other stars have planets, and we started finding more of them in ever-increasing numbers. Mayor and Queloz shared the 2019 Nobel Prize in Physics for that discovery. Now G-stars live for about 10 billion years on the main sequence. Our Sun is halfway through its life. When it finishes fusing hydrogen in its core, in about 5 billion years, it will start to change. And the changes will be dramatic. Let me talk about the death of a Sun-like star, because it's one of the most beautiful and interesting processes in astrophysics. When a G-star like the Sun runs out of hydrogen in its core, it doesn't just switch off. Instead, it goes through a series of stages that transform it from a stable main sequence star into something quite different. The first stage is called the subgiant phase. As hydrogen fusion in the core stops, the core contracts under gravity. This contraction heats up the layer of hydrogen just outside the core, so much so that hydrogen starts fusing in a shell around the inert helium core. This shell fusion produces more energy than the previous core fusion, so the star's outer layers start to expand and cool. The star gets bigger and redder over the course of a few 100 million years. It's still recognizably the same star, but it's changing. Then comes the red giant phase. The star continues to expand, becoming much larger than it was during its main sequence life. Our Sun, when it becomes a red giant, will swell up until its outer edge reaches somewhere around the orbit of Earth, maybe past Earth. The exact details depend on how much mass the Sun loses through stellar winds during the transition. But even if the Sun doesn't quite engulf Earth, the heating and radiation will make Earth completely uninhabitable. The oceans will boil away. The atmosphere will be stripped off. The surface will be sterilized. Long before the sun physically touches Earth, Earth will already be a dead, molten world. During the red giant phase, the star's core keeps contracting and heating up. Eventually, the core gets hot enough that helium starts to fuse into carbon in a process called the triple alpha process because it involves 3 helium nuclei, which are also called alpha particles merging together. When helium fusion ignites in the core of a red giant, it happens dramatically. In stars less than about twice the mass of the sun, it happens in an event called the helium flash, which is not visible from outside the star because it's buried deep in the interior. But it's a sudden, explosive release of energy over the course of maybe a few minutes to a few hours that transforms the star's internal structure. After the helium flash, the star settles into a new equilibrium. It's now fusing helium in its core and hydrogen in a shell around the core. This is called the horizontal branch phase. The star is somewhat smaller and hotter than it was as a red giant, though still much larger and cooler than it was on the main sequence. The horizontal branch lasts for about 100 million years, roughly. During this time, the star is stable, but it's living on borrowed time. Helium fusion is much less efficient than hydrogen fusion, so it burns through helium much faster than it burned through hydrogen. When the helium in the core runs out, the star enters another phase, called the asymptotic giant branch. Now it has an inert carbon-oxygen core with a shell of helium fusion around it and a shell of hydrogen fusion around that. It's like an onion with different layers doing different things. And this configuration is unstable. The star starts to pulsate. It expands and contracts on timescales of years or decades. And during these pulsations, it sheds huge amounts of mass into space, great blobs of gas expanding outward from the star, forming shells around it. Eventually, after tens of thousands of years of this pulsation and mass loss, the star has thrown off most of its outer envelope. What's left is a small, extremely hot core surrounded by expanding shells of gas that it recently ejected. And now, something beautiful happens. The exposed hot core, which is still contracting and heating up, emits intense ultraviolet radiation. This radiation ionizes the surrounding shells of gas, causing them to glow. The result is called a planetary nebula, which is a terrible name because it has nothing to do with planets. The name comes from early telescopic observations when astronomers noticed that these glowing shells of gas looked in low-resolution views kind of like planets, round and colorful, and roughly disc-shaped, so they called them planetary nebulae. And the name stuck, even though we now know they're completely unrelated to planets. Planetary nebulae are some of the most photogenic objects in the sky. The Ring Nebula in the constellation Lyra, the Cat's Eye Nebula in Draco, the Helix Nebula in Aquarius. These are all planetary nebulae, and they're stunning to look at. Symmetrical, colorful, intricate shells of gas surrounding a small, hot central star. They represent the death throes of stars like our sun. What we're going to look like sort of 5 billion years from now. But the planetary nebula phase doesn't last long, only about 10,000 years or so. On cosmic timescales, that's really short. The nebula expands, dilutes, and eventually disperses into the interstellar medium. And what's left is just the exposed core of the former star, a dense, hot, small object called a white dwarf. Let me talk about white dwarfs in some detail because they're one of the most important types of stellar remnant in the universe. And they're not stars in the traditional sense. They're not fusing anything. They're just the leftover cores of dead stars. But they're often included in discussions of types of stars. So I'll include them here. A white dwarf is what's left when a low to intermediate mass star, meaning a star that started its life with less than about 8 times the mass of the Sun, finishes going through the red giant phase and sheds its outer layers. The remaining core is about the size of Earth, but it contains roughly the mass of the Sun, which makes it incredibly dense. A teaspoon of white dwarf material would weigh several tons on Earth. The atoms in a white dwarf are packed together so tightly that they've essentially lost their normal structure. The electrons are no longer bound to individual nuclei. Instead, they form a kind of dense electron soup called degenerate matter that supports the whole star against gravitational collapse. Degenerate matter is weird. It's supported not by thermal pressure like normal gas, but by quantum mechanical effects. Specifically, by the Pauli exclusion principle, which says that no two electrons can occupy the same quantum state. As you try to squeeze electrons closer together, they resist, not because they repel each other electrostatically, though they do that too, but because they can't be in the same state as each other. This creates an outward pressure that supports the star, and it doesn't depend on temperature, which is important because it means a white dwarf can cool down indefinitely and still not collapse. White dwarfs are extremely hot when they first form. The exposed core of a former Sun-like star can have a surface temperature of over 100,000 degrees Celsius. That's why they glow white, hence the name. Over time, they cool. They radiate away their heat into space. But because they have no source of energy, no fusion happening, no gravitational contraction, they just get gradually cooler and dimmer. Over billions of years, they fade from white to yellow to red. And after an unimaginably long time, they should theoretically fade to a black dwarf, a cold, dark, dense remnant that no longer emits significant light. But here's the thing, no black dwarfs exist yet. The universe isn't old enough. Cooling a white dwarf to invisibility takes something like a quadrillion years. That's 1,000,000 billion years. The universe is only 13.8 billion years old. Every white dwarf that has ever formed is still radiating heat, still visible, at least in principle. Black dwarfs are a theoretical prediction about the far future, not an actual observed type of object. There's a mass limit for white dwarfs called the Chandrasekhar limit. It's about 1.4 times the mass of the Sun. If a white dwarf somehow gains mass, from a companion star for instance, and exceeds this limit, it can't be supported by electron degeneracy pressure anymore. And it collapses, sometimes catastrophically, in a specific kind of supernova explosion called a Type 1a supernova, which is important because Type 1a supernovae are used as standard candles for measuring distances in the universe. They all explode with roughly the same intrinsic brightness because they all happen at roughly the same mass. So if you see a Type 1a supernova in a distant galaxy and you measure how bright it appears, you can calculate how far away it is. This technique is a huge part of how we measure the expansion of the universe. It's how we discovered dark energy in the late 1990s. Sirius B is a famous white dwarf. Sirius is the brightest star in the night sky, and it's actually a binary system. Sirius A is a bright A star, main sequence, roughly twice the mass of the Sun, and Sirius B is a white dwarf in orbit around Sirius A. Sirius B was discovered in 1862 by Alvan Graham Clark, who was testing a new telescope, and noticed a faint companion to Sirius. Later analysis showed that Sirius B is incredibly dense and hot and small. It was the first white dwarf ever identified, which means it was the first evidence that stars can end up in this weird, degenerate state. Other well-known white dwarfs include Procyon b, the companion to Procyon, and Van Maanen's star, which is a solitary white dwarf about 14 light-years away. Van Maanen's star was the first isolated white dwarf discovered, meaning one not in a binary system. It's an old, cool white dwarf, and it's interesting because its atmosphere shows evidence of pollution from heavy elements which shouldn't be there. The most likely explanation is that Van Maanen's star is eating the debris from destroyed planets, which is both fascinating and slightly horrifying. Some of the elements we see in its atmosphere match what you'd expect if it had recently consumed a small rocky body, like an asteroid or a small planet. The white dwarf, over time, has been slowly devouring the remains of its own planetary system, which is what our sun will do too, eventually. After the sun becomes a white dwarf, it will slowly, over billions of years, consume the debris of the dead solar system it used to illuminate. Anyway, white dwarfs. Very cool, very weird, very important. Let me move back up the mass scale. F stars are the next category above G stars. They have masses between about 105 and 140% of the sun's mass. Surface temperatures between about 6,000 and 7,500 degrees Celsius. They're yellow-white in color, slightly hotter and bluer than the sun. F stars live shorter lives than G stars, maybe 3 to 7 billion years on the main sequence compared to 10 billion for the sun. Because they're more massive, they burn through their fuel faster. That's the general rule for stars, by the way. The more massive a star is, the shorter its life. Which is counterintuitive because you'd think more fuel means longer life. But more mass means much more intense gravity, which means much higher core temperatures, which means much faster fusion. And the increase in fusion rate outweighs the increase in fuel supply by a lot. So massive stars burn out fast, really fast, in the case of the most massive ones. But we'll get to that. Procyon is a famous F star, while Procyon A is the F star. Procyon B, as I mentioned, is a white dwarf. Procyon A is one of the brightest stars in the night sky, and it's about 11 light years away. It's an F5 star, so it's near the middle of the F category. It's about 40% more massive than the sun and about 7 times more luminous. And it's a subgiant, meaning it's just starting to leave the main sequence and evolve toward the red giant phase. So it's an older F star, past its prime. Sigma Bovis is another F star, and it's often used as a solar analog of sorts, though it's more luminous than the sun. F stars are useful in astronomy because they're bright enough to see easily, but not so massive that they evolve too quickly to be useful for study. They're often used as calibration stars for other kinds of measurements. Above F stars, we have A stars, masses between about 140 and 210% of the sun's mass. Surface temperatures between about 7,500 and 10,000 degrees Celsius. White in color. A star's live for about 1 to 3 billion years on the main sequence. Sirius A is an A star. As I mentioned, it's a binary companion to Sirius B, the white dwarf. Sirius A itself is an A1 star, so near the hot end of the A category. It's about twice as massive as the sun and 25 times more luminous. Its intrinsic brightness, combined with its relatively close distance of 8.6 light years, is why it appears so bright in our sky. Vega is another A star, and probably the most famous one. It's an A0 star at the very hot end of the A category. It's about 25 light years away, and it was historically important in astronomy because it was used as a photometric standard. For a long time, Vega's brightness was defined to be exactly magnitude 0 in the photometric system. All other stars were measured relative to Vega. This has since been refined, and modern systems don't rely exclusively on Vega, but it was the reference star for a very long time. Vega is also famous for a couple of other reasons. It's one of the closest and brightest stars, so it's a natural target for studies of debris disks. And indeed, Vega has a substantial debris disk around it, first detected in 1983 by the IRS satellite. That detection was one of the first indications that other stars have circumstellar material, similar to our own asteroid belt and Kuiper belt. Whether Vega has planets is still an open question. There have been various tentative detections, but nothing definitively confirmed. Vega is also the star that features prominently in Carl Sagan's novel Contact and the movie based on it. In the story, the first extraterrestrial radio signal that humans detect comes from Vega, which was Sagan's choice partly because Vega is famous and recognizable, and partly because Vega is close enough that a radio signal could plausibly reach us in a reasonable amount of time. Fomalhaut is another A star, about 25 light years away, and it's famous for having a very prominent debris disk that was directly imaged by the Hubble Space Telescope in 2008. There was also a claimed direct imaging detection of a planet around Fomalhaut called Fomalhaut b at around the same time. The status of that detection has been controversial. Some later analyses suggested that what was seen wasn't a planet at all, but a dust cloud, possibly from a collision between two large bodies in the debris disk. So the current understanding is that Fomalhaut b was probably not a real planet, but rather an expanding cloud of debris. Altair is another notable A star, and it's one of the closest bright stars to us, at about 17 light years away. Altair is famous for rotating extremely fast. Its equatorial rotation speed is about 286 kilometers per second, which is fast enough that the star is significantly flattened. Its equatorial diameter is about 20% larger than its polar diameter. If you could see Altair up close, it would look like a squashed ball, not a sphere. This rapid rotation also affects the temperature distribution across its surface. The equatorial regions, which are farther from the center, are cooler than the polar regions. So Altair has a bright polar hotspot and a cooler equatorial belt. This effect is called gravity darkening, and it's been observed in Altair using interferometry. Stars are also notable for being the type of star that hosts many of the classical variable stars called delta Scuti variables. These are stars that pulsate on short timescales, typically hours, and their brightness varies slightly during the pulsations. Delta Scuti stars are used as tools for studying stellar interiors through a technique called asteroseismology. By analyzing the frequencies of the pulsations, astronomers can infer information about the star's internal structure, similar to how seismologists on Earth use earthquake waves to study the interior of our planet. Above Eris stars, we have B stars, masses between about 210 and 1,600% of the Sun's mass. So B stars can be huge, really huge, at the top end of the range. Surface temperatures between about 10,000 and 30,000 degrees Celsius. Blue-white in color, though the blueness is subtle to the human eye. B stars live for about 10 million to about a billion years on the main sequence, which is quite short by stellar standards. Rigel is a famous B star, though it's actually a B supergiant, not a main sequence B star. We'll get to supergiants in a bit. Regulus, the brightest star in the constellation Leo, is a main sequence B star. It's a B8, so near the cool end of the B category. It's about 3 to 4 times the mass of the Sun and about 300 times more luminous. And it rotates very fast, similar to Altair. Its rotation period is only about 16 hours, compared to about 25 days for the Sun. This rapid rotation causes it to be significantly flattened at the poles. Spissa, the brightest star in Virgo, is a B star. Or more precisely, Spissa is a binary system, with both components being B stars. The two stars orbit each other every 4 days, and they're close enough that they gravitationally distort each other. Spica is about 260 light-years away. The Pleiades, which is a famous star cluster in the constellation Taurus, contains a lot of B stars. When you look at the Pleiades with the naked eye, you can see maybe 6 or 7 stars, arranged in a distinctive dipper-like shape. But through a telescope, you can see hundreds of stars in the cluster, many of them hot. Young B stars. The Pleiades is a young cluster, only about 100 million years old, which is why so many of its stars are still hot B stars. Older clusters have lost their massive stars to death by supernova, but the Pleiades hasn't had time yet. Whoa. B stars are also often associated with something called B stars, which are B stars that show emission lines from a surrounding gas disk. The E in B stands for emission. These stars rotate very rapidly, close to their breakup speed, and they periodically shed material from their equators, forming a decretion disk, meaning a disk of material flowing outward from the star. B stars are variable and can undergo dramatic changes over years or decades, sometimes losing their disks entirely and then rebuilding them. Above B stars, we have O stars, the hottest and most massive main sequence stars. Masses from about 15 times the Sun up to about 90 times, or in extreme cases, up to about 150 times. Surface temperatures above 30,000 degrees Celsius, sometimes exceeding 50,000 degrees. Blue in color, though so hot that they emit most of their light in the ultraviolet, which we can't see. O stars are rare, really rare. They make up less than 0.00003% of stars in the galaxy. That's 3 in every 10 million stars, or something like that. But they punch way above their weight. O stars are incredibly luminous. A typical O star can be 1,000,000 times more luminous than the Sun. Their intense radiation dominates their surroundings, ionizing huge regions of interstellar gas and creating what are called H2 regions, or emission nebulae, which glow in visible light due to the ionization. The most famous emission nebulae, like the Orion Nebula, are lit up by O stars. O stars are also incredibly short-lived. The most massive O stars can burn through their hydrogen fuel in just a few million years, which is a blink of an eye cosmically. Compared to the trillion-year lifespans of red dwarfs, or the 10 billion-year lifespan of the Sun, O stars are like mayflies. They flare into existence, blaze intensely for a moment, and die. Zeta Ophiuchi is a notable O star, about 366 light-years away. It's an O 9.5 star, so at the cool end of the O category. It's a runaway star, meaning it's moving through the galaxy very fast, at about 24 kilometers per second relative to the surrounding interstellar medium. As it plows through this gas, it creates a bow shock, a curved wave of compressed material in front of the star. The bow shock of Zeta Ophiuchi is visible in infrared images, and it's a striking sight, a huge arcing shockwave being pushed ahead of the fast-moving star. Zeta Puppis is another well-known O star, and it's one of the brightest and most luminous stars visible from Earth in the ultraviolet. It's about 1,000 light years away. It's an O4 star, so quite hot, with a surface temperature of about 40,000 degrees. And it's about 60 times the mass of the Sun and hundreds of thousands of times more luminous. Theta 1 Orionis C is the O star at the heart of the Orion Nebula. It's the brightest of the four young stars called the trapezium, and its intense ultraviolet radiation is what lights up the entire Orion Nebula, making it visible as a glowing pinkish patch even to the naked eye on a dark night. Theta 1 Orionis C is about 40 times the mass of the Sun and around 250,000 times more luminous. And it's very young, only about 2 million years old. It hasn't even settled into a stable main sequence configuration yet. Now, above the main sequence, we have the giants and supergiants. These are the stars that have evolved off the main sequence, or in some cases are so massive that they're always huge and bright throughout their lives. Let me talk about the different flavors of giants and supergiants. Red giants, as I discussed earlier, are stars that have finished fusing hydrogen in their cores and have swelled up to enormous sizes. A typical red giant is 10 to 100 times the diameter of the Sun. Some are much larger. Their surface temperatures are cool, similar to red dwarfs, in the range of 3,000 to 4,000 degrees Celsius. But because they're so large, they're much more luminous than red dwarfs. Thousands of times more luminous than the Sun in many cases. Arcturus is probably the most famous red giant. It's the brightest star in the constellation Bootes, and the fourth brightest star in the entire night sky. It's about 37 light years away, and it's about 25 times the diameter of the Sun and about 170 times more luminous. Arcturus is a K 1.5 giant, so near the boundary between the K and M spectral classes. It's an older star, past its main sequence life, in the red giant phase. Aldebaran, the eye of Taurus the bull, is another famous red giant. It's a K5 giant about 65 light years away and about 45 times the diameter of the Sun. Aldebaran is often mentioned in science fiction, and it's one of the destinations that the Pioneer 10 spacecraft is nominally headed toward, though it will take about 2 million years to get there, and by then Aldebaran will have moved somewhere else, because the stars aren't stationary relative to each other on those timescales. Above red giants, we have supergiants. And this is where things get really extreme. Supergiants are stars with masses greater than about 8 to 10 times the mass of the Sun, which have evolved off the main sequence and become truly enormous. They can be hundreds to thousands of times the diameter of the Sun. They're incredibly luminous, tens of thousands to millions of times more luminous than the Sun. And they're relatively short-lived, existing as supergiants for only a few million years before they explode as supernovae. Supergiants come in different flavors depending on their temperature. Red supergiants are the cool ones, blue supergiants are the hot ones, and there are yellow and white supergiants in between. Betelgeuse is the most famous red supergiant. It's the bright reddish star in the shoulder of Orion. It's about 550 light years away, though the distance has been contested and various measurements give somewhat different values. Betelgeuse is enormous. If you place it at the center of our solar system, its outer edge would extend past the orbit of Mars, possibly past the orbit of Jupiter. It's about 700 to 900 times the diameter of the Sun, and it's about 100,000 times more luminous. Betelgeuse is also famous for having gone through an unusual dimming event in late 2019 and early 2020, sometimes called the Great Dimming. Its brightness dropped by about a factor of 2 over the course of a few months, which was noticeable even to the naked eye. There was a lot of speculation that Betelgeuse might be about to go supernova, which would have been a spectacular event. A supernova only 500 or so light years away, bright enough to be visible in daylight. But it didn't happen. Later analysis suggested that the dimming was caused by a large ejection of gas and dust from the star, which formed a temporary cloud that partially obscured the view. Betelgeuse has since returned to its normal brightness. It will eventually go supernova, probably within the next 100,000 years or so, but maybe not for another million years. On these timescales, we can't really predict it precisely. Antares is another famous red supergiant. It's the brightest star in Scorpius, and its name means, roughly, rival of Mars, because of its reddish color. Antares is about 550 light years away, similar to Betelgeuse, and about 700 times the diameter of the Sun. It's a bit more massive than Betelgeuse, and it will also eventually go supernova. V Canis Majoris is one of the largest known stars. It's a red hypergiant, which is like a supergiant but even more extreme. It's about 3,900 light years away, and its size estimates have varied over the years, but the current best estimates put it at around 1,400 times the diameter of the Sun. If placed at the center of our solar system, its outer edge would extend past the orbit of Saturn. It's shedding mass at a tremendous rate, in a series of outbursts, and it's surrounded by a complex nebula of ejected material. UY Scuti has sometimes been claimed to be the largest known star, at around 1,700 times the diameter of the Sun, though the exact size is uncertain. Stephenson 2-18 has also been suggested as possibly the largest known star at around 2,150 times the diameter of the Sun, though these measurements are hard and contested. The uncertainty is because red supergiants don't have sharp surfaces. Their outer atmospheres are diffuse and extended, so where exactly you draw the boundary of the star is a matter of definition. Blue supergiants are hotter, bluer versions of the same phenomenon. Rigel is a famous blue supergiant. It's the bright blue-white star in the foot of Orion, and it's about 860 light years away. Rigel is about 21 times the mass of the Sun and about 120,000 times more luminous. It's a B8 supergiant, so at the cool end of the B category. Deneb is another famous blue supergiant in the constellation Cygnus, and it's one of the 3 stars of the Summer Triangle. Deneb is remarkably distant, at about 2,600 light years away, and the fact that it appears bright to us despite that enormous distance means it must be incredibly luminous intrinsically. Estimates put it at around 200,000 times the luminosity of the Sun, though the exact value depends on the distance measurement. Above blue supergiants, we have blue hypergiants. And these are the extreme end of the mass range. Stars like Eta Carinae, which is a system in the constellation Carina, about 7,500 light years away. Eta Carinae is a binary system with the primary star being about 100 times the mass of the Sun, or maybe more, and the secondary being about 30 times the mass of the Sun. In the 1840s, Eta Carinae underwent what's called the Great Eruption, in which it briefly became the second brightest star in the sky, despite being 7,500 light years away. During this eruption, it ejected an enormous amount of mass, which formed the Homunculus Nebula, a distinctive bipolar cloud of gas that's still expanding around the star. Eta Carinae is expected to eventually go supernova, or possibly hypernova, and it's one of the stars most closely watched for signs of impending explosion. Another extreme star is Pistol Star, near the center of the galaxy. It's a blue hypergiant about 25,000 light years away, deeply embedded in dust so we can only see it in infrared. It's estimated to be about 27 times the mass of the Sun and something like 1.6 million times more luminous. It's near the theoretical upper limit for how luminous a stable star can be, called the Eddington limit, beyond which the radiation pressure from the star's own light would blow it apart. Yikes. R13601 is often cited as the most massive known star. It's located in the Tarantula Nebula in the Large Magellanic Cloud, which is a satellite galaxy of our Milky Way. R13601 is estimated to be about 200 to 300 times the mass of the Sun, though estimates vary, and it's about 4 to 8 million times more luminous than the Sun. It's the sort of star that shouldn't really be able to exist in some theoretical models. Its intense radiation should blow away its own mass. But it exists anyway, which suggests our models of the most massive stars are incomplete. There's also a special category of extremely luminous, extremely massive stars called Wolf-Rayet stars. These are hot, massive stars that are losing mass at prodigious rates through stellar winds. They've stripped away most of their hydrogen envelopes, exposing the deeper layers where helium or heavier elements dominate the composition. Wolf-Rayet stars are named for the two French astronomers who first described them in 1867. They're extremely rare, but they're important because they're the immediate progenitors of some kinds of supernovae. When a Wolf-Rayet star runs out of fuel and collapses, it often produces a supernova with distinctive properties. WR124 is a notable Wolf-Rayet star that was one of the first targets of the James Webb Space Telescope. The Webb images of WR124 show it surrounded by a beautiful cloud of ejected material glowing in infrared, illustrating the mass loss process directly. Okay, I've been talking about stars by their spectral types and their evolutionary stages. Let me now talk about some special categories of stars that don't fit cleanly into the main sequence framework, or that have unusual properties. Variable stars are stars whose brightness changes over time, and there are many different kinds. I mentioned delta Scuti stars, which pulsate on timescales of hours. There are also Cepheids variables, which are giant stars that pulsate on timescales of days to weeks. Cepheids are incredibly important in astronomy because they have a well-defined relationship between their pulsation period and their intrinsic luminosity. This means that if you measure a Cepheid's pulsation period, you can calculate its luminosity and then compare that to its apparent brightness to figure out how far away it is. This makes Cepheids standard candles, similar to Type 1a supernova, but for shorter distances. They're how we first started measuring the distances to other galaxies. Edwin Hubble used Cepheid variables to prove in the 1920s that the Andromeda Nebula was actually a separate galaxy far outside the Milky Way. Before Hubble, there was a famous debate, sometimes called the Great Debate, between astronomers Harlow Shapley and Heber Curtis about whether the spiral nebulae were part of the Milky Way or separate island universes of their own. Hubble's measurement of Cepheids in Andromeda settled the debate. Andromeda was much too far away to be part of the Milky Way. It was a galaxy in its own right. And suddenly the universe was much, much bigger than anyone had thought. Delta Cephei is the prototype Cepheid variable in the constellation Cepheus. It's the star that gave the whole class its name. Delta Cephei pulsates with a period of about 5.37 days, and its brightness varies by about a factor of 2 during each cycle. Polaris, the North Star, is also a Cepheid variable, though a relatively low amplitude one. Its brightness varies by only a few percent, and its pulsation period is about 4 days. Then there are RR Lyrae variables, which are similar to Cepheids but older and less luminous. They're common in globular clusters and in the halo of the galaxy. They're also used as standard candles for measuring distances within the Milky Way. Mira variables are a class of pulsating red giants that undergo large brightness changes on timescales of months. They're named for the star Mira in the constellation Cetus, which was one of the first variable stars discovered. Mira's brightness varies by a factor of several hundred over a period of about 332 days. At maximum, it's visible to the naked eye. At minimum, you need a telescope to see it. Mira and its cousins are pulsating in the late stages of their lives as they approach the planetary nebula phase. Cataclysmic variables are a whole different beast. These are binary systems in which a white dwarf is stealing material from a companion star. The stolen material accumulates on the white dwarf's surface, and periodically, when enough has built up, it ignites in a thermonuclear runaway, causing a bright flash called a nova. The word nova comes from the Latin for new star, because to ancient observers, these flashes look like new stars appearing in the sky. A nova can brighten by a factor of thousands or more, then fade over the following weeks or months. Novae recur. A given system can produce many novae over its lifetime if the mass transfer from the companion continues. Not to be confused with supernovae, which are much more energetic and generally not recurring events for a given star. Symbiotic stars are another kind of interacting binary in which a hot white dwarf or subdwarf orbits a red giant. The red giant sheds material that's ionized by the hot companion, producing a complex spectrum that shows both cool giant features and hot ionized features simultaneously, hence the name symbiotic. It's a symbiosis between two very different types of stars. Let me talk about neutron stars because they're one of the most extreme types of stellar remnants in the universe. When a star that's initially more massive than about 8 to 10 times the mass of the Sun runs out of fuel, its core collapses. Unlike lower mass stars, which end up as white dwarfs, these more massive stars have cores too massive to be supported by electron degeneracy pressure. The core collapses further, past the point where electrons can support it, and something remarkable happens. The electrons are forced into the protons, converting them into neutrons through a process called electron capture. The whole core essentially turns into a giant ball of neutrons. The result is a neutron star, an object with about 1.4 to about 2 or 2.5 times the mass of the Sun, but compressed into a sphere only about 20 kilometers across, which is roughly the size of a large city. The density of a neutron star is unimaginable. A sugar cube of neutron star material would weigh about 1 billion tons. If you could somehow bring a piece of neutron star matter to Earth, it would immediately explode with the force of a nuclear weapon, because at Earth's much lower ambient pressure, the neutrons would rapidly decay back into protons and electrons, releasing enormous amounts of energy. Neutron stars are supported not by electron degeneracy pressure like white dwarfs, but by neutron degeneracy pressure, which is stronger, and by the strong nuclear force, which begins to become repulsive at extremely short distances. The physics of neutron star interiors is one of the most active areas of research in modern astrophysics. We don't fully understand what happens inside a neutron star. There might be exotic states of matter, like quark matter or hyperon matter, in the deepest cores. Neutron stars are formed in the supernova explosions of massive stars. The collapse of the core releases enormous amounts of energy, most of it in the form of neutrinos, which stream out and drive the outer layers of the star outward in the supernova explosion. The neutron star is left behind at the center, spinning rapidly and with an incredibly strong magnetic field. The rapid spin is because of conservation of angular momentum. When a star's core, which is originally maybe a few thousand kilometers across, collapses to a neutron star only 20 kilometers across, its rotation speeds up dramatically. Newborn neutron stars can rotate hundreds of times per second. The fastest known neutron stars, called millisecond pulsars, spin more than 700 times per second, which means their equatorial surfaces are moving at a significant fraction of the speed of light. Pulsars are neutron stars that we observe as pulsating radio sources. As they rotate, they emit beams of radio waves from their magnetic poles, and if one of those beams happens to sweep across Earth as the star rotates, we see a pulse of radio waves once per rotation, like a lighthouse. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish. They initially called the signal LGM1, half-jokingly for little green men, because the regularity of the pulses was so precise that it briefly seemed possible it might be an alien signal. It wasn't. It was a rotating neutron star, and soon many more were found. Pulsars are the best clocks in the universe. Their pulse timings are so regular that they rival atomic clocks in precision over long timescales. Millisecond pulsars, in particular, are used as precision timing references for a variety of astrophysical experiments, including efforts to detect gravitational waves through pulsar timing arrays. The idea is that if a passing gravitational wave stretches and compresses space-time between us and a pulsar, it should slightly alter the pulse arrival times in a way that can be detected by monitoring many pulsars over many years. The Crab pulsar is a famous pulsar at the center of the Crab Nebula. The Crab Nebula is the remnant of a supernova that was observed by Chinese and other astronomers in 1054 AD. And at the center of the nebula is a pulsar spinning about 30 times per second, powering the whole nebula with its rotational energy. The pulsar has been slowing down measurably since it was discovered, and this slowdown provides the energy that keeps the nebula glowing. Magnetars are a special class of neutron stars with extremely strong magnetic fields, millions of times stronger than ordinary pulsars, which is already millions or billions of times stronger than any magnetic field we can produce on Earth. Magnetars are the objects with the strongest known magnetic fields in the universe. Their fields are so strong that they distort the very atoms in their vicinity, stretching electron orbitals into elongated shapes. If you got close to a magnetar, closer than about 1,000 kilometers, the magnetic field would disrupt the biochemistry of your body, unraveling proteins and disrupting molecular bonds, killing you long before you got close enough for tidal forces to become an issue. Magnetars occasionally undergo starquakes, in which their crusts crack and shift, releasing enormous bursts of X-rays and gamma rays. The most extreme of these, called giant flares, can be detectable across intergalactic distances. In 2004, a giant flare from a magnetar called SGR 1806-2O 50,000 light years away, was so intense that it briefly disturbed Earth's upper atmosphere, despite the enormous distance. If a similar flare occurred from a magnetar within a few light years of Earth, it could potentially cause a mass extinction. Above neutron stars, in terms of what happens when a really massive star dies, we have black holes. Black holes form when the core of a very massive star collapses, and the collapse is so extreme that no known force can stop it. The core keeps collapsing, past neutron star density, past any state of matter we know how to describe, until it reaches, at least in classical general relativity, a singularity, a point of infinite density and infinitely curved spacetime. In reality, quantum effects probably prevent an actual singularity, but we don't have a good theory of quantum gravity to describe what really happens. The singularity, or whatever replaces it, is hidden behind an event horizon, a surface at which the escape velocity equals the speed of light. Nothing that crosses the event horizon can escape. Not matter, not light, not information. Once you're inside, you're gone. Stellar mass black holes, the kind formed from collapsing stars, have masses roughly between 3 and 100 times the mass of the Sun. The lower limit is roughly the maximum mass of a neutron star, above which the neutron star collapses further into a black hole. The upper limit is fuzzy and can be higher in some circumstances. Cygnus X1 is a famous stellar mass black hole. It was one of the first objects strongly suspected to be a black hole. It's an X-ray source in the constellation Cygnus, about 7,000 light-years away, and it's part of a binary system with a blue supergiant companion. The black hole is pulling material off the companion star, and that material forms an accretion disk around the black hole, heating up to millions of degrees and emitting X-rays as it spirals inward. The black hole itself has a mass of about 21 times the mass of the Sun. Cygnus X1 was the subject of a famous scientific bet between Stephen Hawking and Kip Thorne, in which Hawking bet against Cygnus X1 being a black hole as a kind of insurance policy. He said that if it wasn't a black hole, at least he'd have won the bet. By 1990, the evidence had become strong enough that Hawking conceded the bet. Before 04 Cygni is another well-known stellar mass black hole system, also in Cygnus. It undergoes periodic outbursts in which the accretion disk becomes unstable and dumps material onto the black hole rapidly, brightening dramatically in X-rays. Its most recent major outburst was in 2015. Then there are intermediate mass black holes, with masses between about 100 and 100,000 times the mass of the Sun. These are less well established as a category. Only a handful have been identified, and their formation mechanism is not entirely clear. And there are supermassive black holes with masses from millions to billions of times the mass of the Sun. These sit at the centers of most large galaxies. Our own Milky Way has a supermassive black hole at its center, called Sagittarius A star, or SGR-AA star, with a mass of about 4 million times the mass of the Sun. It was imaged directly by the Event Horizon Telescope in 2022, producing the second ever direct image of a black hole after the imaging of M87 star, the supermassive black hole at the center of the galaxy M87 in 2019. Supermassive black holes probably don't form from single collapsing stars. They form through some combination of mergers and accretion over cosmic time, though the details of how they got so big so fast in the early universe is one of the big open questions in astrophysics. Now, since your question was about types of stars, and black holes aren't really stars, I've been drifting a bit off topic. Let me return to actual stars and cover a few more categories I haven't mentioned. Brown dwarfs are objects that aren't quite stars. They form like stars by gravitational collapse of clouds of gas and dust, but they don't have enough mass to sustain hydrogen fusion in their cores. The minimum mass for hydrogen fusion is about 7.5% of the Sun's mass, or about 80 times the mass of Jupiter. Below that, you get a brown dwarf. Brown dwarfs can fuse deuterium, a heavy isotope of hydrogen, for a short time in their early lives, and the more massive ones can fuse lithium. But they can't sustain fusion the way real stars do. So they gradually cool over time, radiating away the heat from their formation, and eventually becoming cold and dark. Brown dwarfs are classified into their own spectral types, extending beyond the M dwarfs. The classes are L, T, and Y in order of decreasing temperature. L dwarfs are the hottest brown dwarfs, with temperatures around 1,300 to 2,400 degrees Celsius. T dwarfs are cooler, around 500 to 1,300 degrees Celsius, and Y dwarfs are the coolest, below about 500 degrees Celsius. The coldest known Y dwarf has a temperature of maybe 250 Kelvin, which is roughly minus 20 degrees Celsius, colder than a winter day in most of the northern hemisphere. And this is a star, in the loose sense of being an object formed by stellar processes. Brown dwarfs are hard to find because they're so dim. The first brown dwarf was confirmed only in 1995, the same year that 51 Pegasi b was discovered. It's called Tida 1, and it's in the Pleiades cluster. Since then, many more brown dwarfs have been found, and it's now clear that they're common in the galaxy, possibly as common as stars, though the exact number is still uncertain. The line between the most massive planets and the least massive brown dwarfs is fuzzy. Both are objects with masses of roughly 13 to 80 times Jupiter that don't fuse hydrogen. Deuterium fusion, which happens above about 13 Jupiter masses, is one commonly used dividing line, but it's a bit arbitrary. And formation mechanism is another possible dividing line, but it's not always clear how a given object formed. Anyway, let me cover a few more special categories of stars. There are subdwarfs, which are stars similar to main sequence stars, but with lower metallicity, meaning fewer heavy elements. These are typically old stars from the earlier generations of the galaxy. They're slightly hotter and dimmer than main sequence stars of the same spectral type. Subdwarfs are important for understanding the history of the galaxy because they preserve the composition of the interstellar medium from when they formed long ago. There are subgiants, which are stars in the transition phase between the main sequence and the red giant branch. They've just finished fusing hydrogen in their cores, and they're expanding and cooling on their way to becoming red giants. Procyon A, as I mentioned, is a subgiant. There are horizontal branch stars, which are stars in the phase where they're fusing helium in their cores. These are common in globular clusters, where their properties help date the cluster. There are AGB stars, or asymptotic giant branch stars, which I mentioned earlier, late-stage red giants that are pulsating and shedding mass, on their way to becoming planetary nebulae. There are post-AGB stars, which are the exposed cores of former AGB stars, transitioning to the white dwarf phase. There are Wolf-Rayet stars, which I've already discussed. There are luminous blue variables, or LBVs, which are extremely massive stars that undergo occasional huge eruptions and mass loss events. Eta Carinae, which I mentioned, is one of these. There are S stars, which are red giants with unusual chemical compositions, particularly enriched in heavy elements like zirconium and technetium. The presence of technetium is particularly interesting because technetium has no stable isotopes and decays on relatively short timescales. So its presence in an S star means the star has been actively dredging up freshly synthesized material from deeper layers. There are carbon stars, which are red giants where the ratio of carbon to oxygen has been inverted from the normal stellar composition. Carbon stars have some of the reddest colors in the sky because carbon compounds in their atmospheres absorb strongly in the blue. There are barium stars, which are giants that have unusually high abundances of barium and other heavy elements. They're thought to be the products of mass transfer in binary systems, where a former AGB star transferred enriched material to its companion and then died. So the visible star is showing us the pollution from its now deceased companion. There are blue stragglers, which are stars that appear in old clusters but seem to be too hot and blue for their age. They shouldn't exist. All the hot blue stars in an old cluster should have died long ago. The explanation is usually that blue stragglers are the products of stellar mergers or mass transfer in binary systems, which rejuvenated an older star by giving it fresh fuel. Okay, I think I've covered most of the major types of stars in one way or another. Let me summarize briefly before wrapping up. Stars are classified primarily by their surface temperatures, which correlates with their masses and colors. From coolest to hottest, the main sequence spectral types are MM, K, G, F, A, B, O. Below M dwarfs, we have brown dwarfs, which aren't quite stars. Above the main sequence, we have giants and supergiants of various colors and evolutionary stages. At the end of stellar life, we have white dwarfs, neutron stars, and, for the most massive stars, black holes. There are also many specialized categories of stars with unusual properties or in unusual phases of evolution. The universe is dominated, in terms of numbers, by small, dim red dwarfs. But in terms of light output, the most massive and luminous stars, though rare, contribute a huge fraction of the total. And in terms of importance for the chemistry of the universe, all types of stars matter, because different types produce different elements through different processes. The heavy elements that make up our bodies, the calcium in our bones, the iron in our blood, the oxygen in our lungs, all of it was made in stars. Different elements in different types of stars. Carbon and oxygen mostly in stars a bit more massive than the sun. Iron and heavier elements up to iron in supernovae. Elements beyond iron, like gold and uranium, in neutron star mergers and certain kinds of supernovae. We are, quite literally, star stuff, as Carl Sagan famously put it. Stellar nucleosynthesis is the process by which stars create heavier elements from lighter ones. When the universe first formed, in the aftermath of the Big Bang, the only elements that existed in significant quantities were hydrogen, helium, and trace amounts of lithium. That's it. About 75% hydrogen by mass, about 25% helium by mass, and a tiny sprinkle of lithium and beryllium. Every other element in the periodic table, every carbon atom, every oxygen atom, every iron atom, every gold atom, every uranium atom was made later, inside stars or in the violent events at the end of stellar lives. Understanding how this happened in detail is one of the great achievements of 20th century astrophysics. The story really starts with a famous paper published in 1957 by Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle. The paper is usually called B2FH, after the initials of the authors. And it laid out for the first time a comprehensive theory of how stars could produce essentially all the elements heavier than helium, through a series of specific nuclear processes operating in different stellar environments. The paper was extraordinarily influential. Fowler won the Nobel Prize in Physics in 1983, in part for this work. Hoyle didn't share the Nobel, which many people, including me, think was an injustice. He was one of the greatest astrophysicists of the 20th century, and his exclusion from the Nobel is often attributed to his contrarian personality and his rejection of the Big Bang theory, which, incidentally, he named. Big Bang was originally a somewhat dismissive term that Hoyle used on a radio broadcast, and it stuck. Hoyle was actually a proponent of the steady state theory, which said the universe had no beginning and was continuously creating matter as it expanded. That theory has since been decisively refuted, but Hoyle held to it for most of his life. Anyway, let me talk about the specific nuclear processes. The first and most important process is hydrogen burning. This is what powers main sequence stars, including the Sun. In hydrogen burning, 4 hydrogen nuclei, which are just protons, are combined into one helium nucleus, which contains 2 protons and 2 neutrons. The mass of a helium nucleus is slightly less than the mass of 4 protons. The difference, which is about 0.7% of the original mass, is converted into energy according to Einstein's famous equation E equals mc squared. And this energy is what powers the star. But you can't just smash 4 protons together directly. That's not how it works. The process happens in a series of steps, and there are 2 main pathways depending on the temperature and composition of the star. In stars with masses similar to or less than the Sun, the dominant hydrogen burning process is called the proton-proton chain, or the PP chain. It starts when 2 protons collide with enough energy to overcome their mutual electrostatic repulsion and fuse. This is extremely difficult because protons repel each other electrically, and you have to get them close enough for the strong nuclear force to take over. In the core of the Sun, temperatures are about 15 million degrees Celsius, and even at that temperature, the average proton doesn't have nearly enough kinetic energy to overcome the electrostatic barrier. Fusion happens anyway, but only because of quantum tunneling. Protons can occasionally tunnel through the electrostatic barrier and reach each other. This is a rare event for any given pair of protons, but the Sun contains an enormous number of protons, and even rare events happen frequently when you have that many participants. When 2 protons fuse, they don't stay as a diproton, which would be unstable. One of the protons decays into a neutron, emitting a positron and a neutrino, and the result is a deuteron, which is a nucleus containing 1 proton and 1 neutron. This is deuterium, the heavy isotope of hydrogen. The step where a proton turns into a neutron requires the weak nuclear force, which is much slower than the strong force. This is what makes the PP chain slow. The initial proton-proton fusion is the bottleneck. On average, a given proton in the Sun's core waits about 10 billion years before it undergoes fusion, which is why the Sun burns for so long. If the reaction were faster, the Sun would burn out much more quickly. Once you have a deuteron, the next step is faster. The deuteron reacts with another proton to form helium-3, a nucleus with 2 protons and 1 neutron. Then 2 helium-3 nuclei collide to form helium-4, the ordinary form of helium, releasing 2 protons in the process. So the net result of the PP chain is that 4 protons become 1 helium-4 nucleus, plus some positrons, neutrinos, and gamma-ray photons that carry away the energy. The neutrinos in particular are important. They stream out of the sun's core at nearly the speed of light and pass through the sun's overlying layers almost without interacting. So they reach the surface in a few seconds and then they head off into space. About 65 billion solar neutrinos pass through every square centimeter of Earth every second. Most of them pass straight through you without interacting. Solar neutrinos have been detected on Earth by various experiments starting in the late 1960s, and they've been a crucial test of our understanding of the Sun. Actually, there's a whole subplot here worth mentioning called the solar neutrino problem. When the first solar neutrino experiments were done by Ray Davis at the Homestake Mine in South Dakota, starting in 1968, they found only about a third as many neutrinos as theory predicted. This was a major puzzle for decades. Either the models of the Sun were wrong, or something was happening to the neutrinos on their way from the Sun to Earth. The mystery was resolved in the late 1990s and early 2000s when it was discovered that neutrinos have mass and they can oscillate between different flavors. There are three flavors of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. The Sun produces electron neutrinos, but by the time they reach Earth, some have oscillated into other flavors. Davis's experiment could only detect electron neutrinos, so it missed the ones that had oscillated away. Once you account for the oscillation, the numbers match theory beautifully. Ray Davis was awarded the Nobel Prize in Physics in 2002 for this work, alongside Masatoshi Koshiba, and later Takaaki Kajita and Arthur McDonald received the 2015 Nobel Prize for definitively demonstrating neutrino oscillation. Okay, back to nucleosynthesis. In stars more massive than the Sun, hydrogen burning happens primarily through a different pathway called the CNO cycle for carbon, nitrogen, oxygen. The CNO cycle uses carbon, nitrogen, and oxygen nuclei as catalysts to convert 4 protons into one helium-4 nucleus. The carbon, nitrogen, and oxygen aren't consumed in the process. They just facilitate the reactions. But you need to have some carbon, nitrogen, or oxygen already present in the star, which is fine for stars that formed from previously enriched interstellar material, but wouldn't have worked for the very first stars in the universe which had no heavy elements. Fantastic. The CNO cycle becomes dominant over the pp chain at temperatures above about 17 million degrees Celsius. Stars more massive than about 1.3 times the mass of the Sun have core temperatures high enough for the CNO cycle to dominate, and the CNO cycle is much more temperature sensitive than the pp chain. Its reaction rate scales roughly as temperature to the 17th power compared to the pp chain, which scales as temperature to the 4th power. This extreme temperature sensitivity has important consequences for the structure of massive stars. It means the energy generation is highly concentrated at the very center of the star, which drives convection in the core, meaning the innermost regions become well mixed by turbulent motion. Once a star has exhausted the hydrogen in its core, it starts to contract, its core temperature rises, and eventually it can start fusing helium. Helium burning is trickier than hydrogen burning because there's no stable nucleus with mass 5 or mass 8. So you can't just add a proton to a helium-4 to get a mass 5 nucleus, or fuse 2 helium-4 nuclei to get a mass 8 nucleus. Both possibilities are dead ends. You have to jump straight from helium-4 to some nucleus with mass 12 or greater. The way this works is called the triple alpha process. 3 helium-4 nuclei, which are also called alpha particles, come together almost simultaneously to form a carbon-12 nucleus. This is a very unlikely event because it requires three particles to collide in the same place at nearly the same time, which is much rarer than two-particle collisions. But at the high densities and temperatures of a helium-burning stellar core, around 100 million degrees Celsius, it happens often enough to power the star. Actually, there's a fascinating story about the triple alpha process, which involves Fred Hoyle again. In the early 1950s, Hoyle was thinking about how the triple alpha process could work, and he realized that the standard version of the reaction was too slow to produce the observed amount of carbon in the universe. There was a fundamental problem. When two helium-4 nuclei combine, they form beryllium-8, which is extremely unstable and decays back into two helium-4 nuclei in about 10 to the minus 16 seconds, which is an incredibly short time. So most beryllium-8 nuclei decay before a third helium-4 can come along and combine with them. Hoyle realized that for the triple alpha process to work at the observed rate, carbon-12 must have a specific excited state at a specific energy level, such that the reaction could proceed through a resonance. A resonance is a situation where the incoming particles have just the right energy to correspond to a natural energy level of the product nucleus, which dramatically increases the reaction rate. Hoyle predicted that carbon-12 should have an excited state at about 7.65 million electron volts above the ground state. This prediction was based purely on the anthropic principle essentially. Hoyle argued that if this excited state didn't exist, carbon wouldn't be produced in stars, and we wouldn't be here to observe the universe. So the excited state must exist. At the time, no such state was known. Hoyle went to William Fowler at Caltech, and Fowler was initially skeptical but agreed to look. Fowler's group did the experiment, and they found the excited state, right where Hoyle had predicted it. This is one of the most famous successful predictions based on anthropic reasoning in the history of science. The state is now called the Hoyle state, and it's crucial for our existence. Without it, the universe would have almost no carbon, no complex chemistry, no life as we know it. Anyway, the triple alpha process produces carbon-12, and then if the temperature is high enough, some carbon-12 can react with another helium-4 to produce oxygen-16. This is the process that produces most of the oxygen in the universe. The ratio of carbon to oxygen produced in a helium-burning star depends sensitively on the temperature and density conditions and on the exact rates of the two reactions involved. The carbon-oxygen ratio is one of the important parameters in stellar nucleosynthesis, and it's still not perfectly known, which has implications for our understanding of stellar evolution and the composition of white dwarfs. Helium burning in the core lasts for about 10% as long as hydrogen burning, roughly. So a star like the Sun, which burns hydrogen for about 10 billion years, will burn helium for about 100 million years. During helium burning, the star is a red giant. Its outer layers are enormous and cool. Its core is compact and hot. Extraordinary. After core helium burning ends, in a star like the Sun, the story gets more complicated. The core, now composed of carbon and oxygen, contracts and heats up, but it doesn't get hot enough to fuse carbon. Fusing carbon requires temperatures of about 500 million to a billion degrees Celsius, and a star has to be more massive than about 8 times the mass of the Sun for its core to reach those temperatures. So for lower mass stars, carbon fusion never happens. The core just contracts until it becomes degenerate, meaning it's supported by electron degeneracy pressure rather than thermal pressure. Meanwhile, hydrogen and helium continue to burn in shells around the inert core. This is the asymptotic giant branch, or AGB, phase, which I mentioned before. And it's where a lot of interesting nucleosynthesis happens in stars like the Sun and slightly more massive. During the AGB phase, the helium-burning shell and the hydrogen-burning shell alternate in dominance in a series of instabilities called thermal pulses. Every so often, the helium shell ignites in a runaway burst, producing a huge amount of energy in a short time, then subsides. Between helium shell flashes, the hydrogen shell dominates. And during the flashes, convection reaches down into the interior of the star and dredges up material from the deeper layers, mixing it with the outer envelope. This dredge-up process is what brings freshly synthesized carbon and other elements to the surfaces of AGB stars. It's what creates carbon stars, S stars, and the various other chemically peculiar giants. The material that gets dredged up depends on the mass of the star and its evolutionary state. And there are actually 3 different dredge-ups that happen at different phases, called first, second, and third dredge-up. More importantly, AGB stars are the site of an important form of nucleosynthesis called the S process, which produces about half of the elements heavier than iron. Let me explain the S process. For elements up to iron, nuclear fusion is exothermic, meaning it releases energy. So stars can make elements up to iron by fusion, and this powers them. But beyond iron, fusion becomes endothermic. It costs energy, so you can't make elements heavier than iron by ordinary stellar fusion. But heavier elements exist. Gold, uranium, lead, all the way up to the artificial super heavy elements. Where did they come from? They come from neutron capture. If you have a nucleus and it captures a free neutron, its atomic mass increases by 1, but its atomic number stays the same. So you get a heavier isotope of the same element. Then, if that isotope is unstable, it can undergo beta decay, in which a neutron inside the nucleus turns into a proton, emitting an electron and a neutrino. This increases the atomic number by 1, so you get a different element one step up the periodic table. By repeated neutron captures and beta decays, you can build up progressively heavier elements. There are 2 main variants of neutron capture nucleosynthesis, distinguished by the rate at which neutrons are captured relative to the rate of beta decays. The S process, or slow neutron capture process, happens in environments where neutrons are relatively scarce, and beta decays generally happen faster than the next neutron capture. So after a nucleus captures a neutron, if it's unstable, it decays back to a stable configuration before capturing another neutron. This means the S process proceeds along the valley of nuclear stability, making stable nuclei step by step, with occasional beta decays to move up the periodic table. The S process happens in AGB stars, where free neutrons are produced by various nuclear reactions in the interiors and slowly build up heavier elements over the course of the star's AGB lifetime. Elements produced in significant quantities by the S process include strontium, barium, lead, and many others. Barium stars, which I mentioned earlier, are stars enriched in S process elements by mass transfer from a former AGB companion. The other variant is the R process, or rapid neutron capture process. This happens in environments with an enormous flux of neutrons, so intense that neutron captures happen faster than beta decays. Nuclei rapidly capture many neutrons in quick succession, becoming extremely neutron-rich and unstable before eventually beta decaying back down toward the valley of stability. The R process can reach very heavy elements, all the way up to uranium and beyond, before the resulting nuclei become too unstable to persist. For a long time, the site of the R process was uncertain. The two main candidates were core collapse supernovae and neutron star mergers. There were theoretical reasons to think both could work, but observational evidence was ambiguous. Then in 2017, the LIGO Gravitational Wave Observatory detected the merger of two neutron stars, called G W170817. This was accompanied by electromagnetic signals across the spectrum, from gamma rays to radio waves, providing a wealth of information about what happens when neutron stars merge. And the observed electromagnetic signal was consistent with the production of large amounts of R process elements in the merger. So it's now generally believed that neutron star mergers are the dominant source of R process elements in the universe, though supernovae may contribute some as well. This means that when you wear a gold ring, the gold in that ring was probably made in a neutron star merger billions of years ago, before the sun and the solar system existed. The debris from that merger was mixed into the interstellar medium and then incorporated into the cloud that eventually formed our solar system. Every gold atom on Earth has that history, which is, I think, kind of incredible to contemplate. Okay, let me continue with stellar nucleosynthesis. For stars more massive than about 8 times the mass of the Sun, carbon fusion can happen in the core after helium burning ends. This is called carbon burning, and it happens at temperatures of about 600 million to a billion degrees Celsius. Carbon burning produces neon, sodium, and magnesium, among other products. After carbon burning, the core contracts and heats up further, and if the star is massive enough, neon burning begins at temperatures of about 1.2 billion degrees Celsius. Neon burning is a bit unusual because it starts with photodisintegration. At these extreme temperatures, the thermal photons in the stellar core have enough energy to break apart neon nuclei, converting some neon into oxygen and helium. The helium then reacts with other neon nuclei to produce magnesium and silicon. So neon burning is really a combination of photodisintegration and helium capture. After neon burning, at temperatures around 1.5 billion degrees, oxygen burning begins. Oxygen nuclei fuse with each other to produce silicon, sulfur, and other intermediate mass elements. Oxygen burning is relatively long-lived compared to the burning stages that come after it, lasting maybe a few months to a year in the most massive stars. After oxygen burning, at temperatures approaching 3 billion degrees Celsius, silicon burning begins. Silicon burning is not really a simple fusion of two silicon nuclei because the Coulomb barrier between two silicon nuclei is too high, even at these temperatures. Instead, silicon burning proceeds through a complex network of photodisintegration and particle capture reactions, in which silicon nuclei are gradually built up into heavier and heavier elements, one nucleon at a time, until they reach iron. Silicon burning happens fast. It lasts only about a day in the core of a massive star before the fuel runs out. And once silicon has been converted into iron and nearby elements, that's the end. Iron is the most tightly bound nucleus in terms of binding energy per nucleon. You can't fuse iron to release energy. Any further fusion would consume energy rather than release it. So the star has no more nuclear fuel to burn. Its core is a hot ball of iron and similar elements with a mass of maybe 1.4 to 2 times the mass of the Sun, supported by electron degeneracy pressure. But that support is unstable. As the star continues to try to burn material in shells around the iron core, more and more iron gets deposited on the core and its mass grows. When it exceeds the Chandrasekhar limit, electron degeneracy pressure can no longer support it, and the core begins to collapse. And this is where the supernova happens. The collapse of the iron core is a catastrophic event. The core falls in on itself at speeds approaching a quarter of the speed of light. In less than a second, it collapses from about the size of the Earth to about 20 kilometers across. As it collapses, several things happen. The high temperatures cause photodisintegration of iron nuclei, breaking them back down into helium nuclei and free neutrons. This actually absorbs energy, which accelerates the collapse. The electrons are squeezed into the protons through inverse beta decay, converting protons into neutrons and releasing neutrinos. This also removes support from the collapse. And eventually the collapse continues until the neutrons come into contact with each other, and neutron degeneracy pressure suddenly halts the collapse, like slamming into a brick wall. The core bounces. And this bounce sends a shock wave outward through the overlying layers of the star. In the simplest models of supernovae, this shock wave carries enough energy to blast the outer layers of the star into space, producing the supernova explosion we observe. But detailed simulations show that the shock wave usually stalls, losing energy to photodisintegration of the material it's plowing through, and doesn't successfully blow up the star on its own. What actually saves the supernova in current models is the neutrinos. The core collapse produces an enormous burst of neutrinos, more than 10 to the 58th neutrinos in total, carrying away 99% of the total energy released by the collapse. Normally, neutrinos barely interact with matter. They pass right through. But at the densities in the collapsing core, even neutrinos interact strongly enough to deposit some fraction of their energy. And this energy deposition in the region behind the stalled shock revives the shock and drives it outward through the star, producing the observed explosion. The details of exactly how this happens are extremely complex, and modeling supernova explosions requires some of the most sophisticated computer simulations in all of science. Three-dimensional simulations including detailed neutrino transport, magnetohydrodynamics, general relativistic effects, and complex nuclear physics. The simulations have made great progress in the last 2 decades, but there's still active debate about the details of how supernova explosions work. Sometimes they succeed in the simulations, sometimes they fail. Which stars produce successful explosions and which quietly collapse to black holes without much of a display is not fully understood. When a supernova does successfully explode, its brightness can rival the entire galaxy that contains it. A single supernova can outshine 100 billion stars for a few weeks. The total energy released is about 10 to the 44th joules, most of it in neutrinos, with about 1% in kinetic energy of the ejected material, and about 0.01% in light, which is still an enormous amount of light. Different types of supernovae have different observational properties, and the classification is based on their spectra and light curves. Type 1 supernovae are those whose spectra don't show hydrogen. Type 2 supernovae are those whose spectra do show hydrogen. Within these, there are subcategories. Type 1a supernovae are the ones I mentioned earlier. They come from white dwarfs that exceed the Chandrasekhar limit, either by accretion from a companion or by merging with another white dwarf. They're the standardizable candles used for cosmology. They don't show hydrogen because white dwarfs don't have much hydrogen, and they show characteristic features of silicon in their spectra. Type 1b and 1c supernovae come from core collapse of massive stars that have lost their hydrogen envelopes, and in the case of IC, also their helium envelopes. These are typically associated with Wolf-Rayet stars, which have shed their outer layers through strong stellar winds before exploding. Some type Ike supernovae are associated with gamma-ray bursts, which are extremely energetic explosions that briefly release more energy than the sun will produce in its entire lifetime. The connection between type Ike supernovae and long-duration gamma-ray bursts was established in the early 2000s and is one of the great achievements of modern astrophysics. Type 2 supernovae are the standard core collapse supernovae from massive stars that retain their hydrogen envelopes. There are subcategories type 2p for those with a plateau in their light curve, type 2l for those with a linear decline, type 2n for those with narrow spectral lines from interaction with circumstellar material, and type 2b for those that transition from type 2 to type 1b as their thin hydrogen layer becomes transparent. There are also more exotic supernova types being discovered. Superluminous supernovas, which are 10 or more times brighter than ordinary supernovae, powered by exotic mechanisms like a rapidly rotating magnetar or interaction with dense circumstellar material. Pair instability supernovae, which are theorized to happen in extremely massive stars above about 130 solar masses, where the production of electron-positron pairs in the core removes pressure support and triggers a runaway thermonuclear explosion that completely destroys the star, leaving no remnant. These are rare in the current universe, but may have been common in the early universe among the first generation of stars. Failed supernovae are events where the core collapse happens, but the shock wave fails to unbind the star, and the star quietly implodes into a black hole. These are hard to observe because they're characterized by the disappearance of a massive star rather than a bright flash. But a few candidates have been identified using surveys that monitor nearby galaxies and look for stars that vanish. Now, historical supernovae observed in our own galaxy or nearby have played a huge role in astronomy. Let me mention some of them. The Crab supernova in 1054 AD produced the Crab Nebula, which I mentioned before. It was observed by Chinese astronomers and possibly by others, including Native American observers. The remnant is one of the best studied objects in the sky. Tycho's supernova in 1572 was observed by Tycho Brahe, and its observation played a role in undermining the ancient Aristotelian view that the celestial realm was unchanging. The fact that a new star appeared where none had been before was clear evidence of change in the heavens. Tycho's supernova was a type 1a supernova, and its remnant is still observable as an expanding cloud of gas. Kepler's supernova in 1604 was observed by Johannes Kepler. It was the last supernova observed in our own galaxy before the invention of the telescope, and, as it turns out, the last supernova observed in our own galaxy at all, up to the present day. It's been more than 400 years since a supernova visible to the naked eye has gone off in the Milky Way. Statistically, we're overdue. Supernovae happen in a galaxy like the Milky Way at a rate of about 2 or 3 per century, on average. So we should have seen several by now. Most probably did go off, but were hidden from view by dust and gas in the galactic plane. When the next Milky Way supernova happens, and someday one will, it will be a huge event for astronomy. Neutrino detectors around the world will detect the neutrino burst hours before the light arrives, giving advance warning. Gravitational wave detectors will look for the signal from the collapse. Telescopes across the electromagnetic spectrum will study it in unprecedented detail. The closest supernova observed in modern times was SN 1987A in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way. It went off in February 1987, and it was the closest observed supernova since Kepler's. About 24 neutrinos from SN 1987A were detected on Earth by 3 different neutrino detectors, confirming the theoretical predictions about the neutrino burst from core collapse. This was a huge triumph for supernova theory. The progenitor star of SN 1987A was identified in pre-explosion images. It was a blue supergiant, Sanduleak -69202, which was somewhat unexpected. Most supernova progenitors were thought to be red supergiants. This discovery led to refinements in the models of stellar evolution and mass loss. SN 1987 A has continued to be observed for decades since its explosion. The ejecta are colliding with a ring of material that was shed by the progenitor star before the explosion, producing a spectacular light show at various wavelengths. And the compact remnant, presumably a neutron star, has been elusive but appears to have been finally detected in the last few years by the ALMA and JWST observatories, buried in the dense inner ejecta. Okay, let me now talk about the interior structure of stars in more detail. Because I've been talking about what happens inside stars, but I haven't really talked about how they're structured. Stars are self-gravitating balls of gas in hydrostatic equilibrium, meaning that at every point inside the star, the outward pressure balances the inward pull of gravity. If pressure were larger, the star would expand. If gravity were larger, it would collapse. The balance between these forces determines the structure of the star. The pressure inside a star comes from several sources. In most stars, most of the time, the dominant source is thermal pressure of the gas, meaning the pressure due to the random thermal motion of atoms, ions, and electrons. Thermal pressure depends on temperature and density. Higher temperature or higher density means higher pressure. In stars that are very hot or that are highly ionized, radiation pressure can also become important. Radiation pressure is the pressure exerted by photons. It scales as temperature to the 4th power, so it becomes rapidly more important at high temperatures. In the most massive stars, radiation pressure can rival or exceed gas pressure in the interior. This has important consequences. Radiation pressure sets an upper limit to the luminosity of stars, called the Eddington limit. Above this limit, radiation pressure would blow away the outer layers of the star. The Eddington limit is what limits the maximum mass of stars, roughly speaking. Stars much above about 150 solar masses would exceed the Eddington limit and blow themselves apart. There are exceptions and complications, but that's the rough idea. In degenerate stars like white dwarfs and neutron stars, the pressure comes from degeneracy pressure, which is a quantum mechanical effect. According to the Pauli exclusion principle, no two identical fermions can occupy the same quantum state. So when you compress a gas of fermions to sufficiently high density, the low energy states get filled up, and the particles are forced into higher energy states. This creates a pressure that resists further compression, and it's largely independent of temperature. Electron degeneracy pressure supports white dwarfs. Neutron degeneracy pressure, along with contributions from the strong nuclear force, supports neutron stars. Energy is transported through the interior of a star by 3 mechanisms: radiation, convection, and conduction. Radiation is the transport of energy by photons. In the deep interior of a star, photons are constantly emitted, absorbed, and re-emitted by the plasma. Each photon travels only a very short distance before being absorbed, and its direction and energy are randomized when it's re-emitted. So the transport of energy from the core to the surface is a slow diffusion process. It takes a photon, on average, about 100,000 years to random walk its way from the core of the sun to the surface, even though the sun's radius is only about 2 light seconds. Once the photon reaches the surface, it flies off into space at the speed of light. But its journey through the interior was slow. Convection is the bulk motion of fluid, carrying heat with it. In parts of a star where the temperature gradient is too steep to be transported efficiently by radiation, convection takes over. Hot parcels of gas rise, cooled parcels sink, and this circulation carries energy outward. Convection is very efficient, and once it's active, it tends to establish a temperature profile very close to what's called adiabatic, meaning the temperature and pressure are related in a specific way that reflects gas being moved around without gaining or losing heat. Different parts of different stars are convective or radiative in different combinations. In the sun, the core is radiative, and the outer 30% by radius is convective. This convective outer layer is what produces the granulated appearance of the sun's surface, where you can see the tops of convection cells rising and sinking. In stars less massive than the sun, the convective region extends deeper. In red dwarfs, which are very low mass, the entire star is convective, meaning the material in the core is continually mixed with material from the surface. This has important consequences. It means red dwarfs never develop the layered onion structure of more massive stars, and they can use their hydrogen fuel more efficiently, prolonging their lifetimes to hundreds of billions or even trillions of years. In stars more massive than the sun, the situation is inverted. The core is convective, driven by the strong temperature sensitivity of the CNO cycle, and the outer regions are radiative. This has consequences for how these stars evolve. The convective core is well mixed, so hydrogen fuel throughout the core is available for burning, extending the main sequence lifetime slightly compared to a purely radiative core. But when the core hydrogen runs out, it does so suddenly across the whole convective region, and the star transitions rapidly to its next evolutionary phase. Conduction is the transport of heat by direct energy exchange between particles, without bulk motion or photon emission. In most stellar plasmas, conduction is negligible compared to radiation and convection, but in degenerate matter, like the interiors of white dwarfs and neutron stars, conduction by electrons can become efficient because degenerate electrons have long mean free paths. Let me now talk a bit about astroseismology, which I mentioned briefly before. This is a really cool field. Astroseismology is the study of oscillations in stars and using them to probe stellar interiors. Stars, it turns out, are ringing. They oscillate in many different modes simultaneously, like a bell struck by many hammers. The sun, for example, is oscillating in millions of modes at once, with periods ranging from minutes to hours. These oscillations are driven by convection in the outer layers, which acts like a random forcing that excites the modes. The oscillations are detected by very precise measurements of the sun's surface, either through Doppler shifts of spectral lines indicating surface motion or through brightness variations. Each oscillation mode probes a different part of the stellar interior. Higher frequency modes are trapped in the outer layers. Lower frequency modes penetrate deeper. By measuring the frequencies of many modes and comparing them to theoretical predictions, we can reconstruct the interior structure of the star, including the sound speed as a function of depth, the composition profile, and the rotation rate at different depths. This is called helioseismology when applied to the Sun, and asteroseismology when applied to other stars. Helioseismology has been enormously successful. It confirmed that the Sun's interior structure matches predictions to remarkable accuracy, provided a strong test of the models that were used to predict the solar neutrino flux, and revealed unexpected features like the tachocline, a thin layer at the base of the Sun's convection zone where the rotation rate changes rapidly. This tachocline is thought to be important for the generation of the Sun's magnetic field. Asteroseismology of other stars was made possible by space missions that could monitor stellar brightness with extreme precision over long periods. The Corot mission, launched in 2006, and the Kepler mission, launched in 2009, revolutionized the field. Kepler in particular, though designed primarily to find exoplanets, provided asteroseismic data on tens of thousands of stars, allowing detailed studies of stellar interiors across a wide range of masses and evolutionary stages. The TESS mission, currently operating, continues this work for stars across the whole sky. One of the great successes of asteroseismology has been characterizing the interior rotation of red giants. Before asteroseismology, we knew how fast the surfaces of stars rotated, but the interiors were essentially opaque to observation. Asteroseismology revealed that red giant cores rotate much faster than their envelopes, which was somewhat expected, but at rates that don't match the predictions of standard stellar models. Some mechanism is transporting angular momentum from the core to the envelope more efficiently than we understand. This is one of the outstanding puzzles in stellar physics right now, and various candidate mechanisms are being investigated, including internal gravity waves, magnetic instabilities, and mixed modes of oscillation that couple the core and envelope. Asteroseismology has also allowed detailed determination of stellar ages, which is otherwise very difficult. Stellar ages are notoriously hard to measure because a star's brightness and color change relatively slowly over its main sequence lifetime. But asteroseismic quantities are sensitive to the size of the helium core, which grows steadily as hydrogen burning progresses. So by measuring the right seismic quantities, you can pin down the age of a star to within about 10%, which is much better than most other methods. Now let me talk about the demographics of stars in the galaxy and how they trace the history of star formation. Because I think this ties together a lot of what I've been discussing here on Signal Floor Channel. Our Milky Way galaxy contains something like 200 to 400 billion stars, distributed in several main structural components. There's the thin disk, which contains most of the stars, and which is the site of ongoing star formation. There's the thick disk, an older population of stars that forms a puffier distribution than the thin disk. There's the bulge, a densely packed region of stars near the galactic center. And there's the halo, an extended distribution of ancient stars that surrounds everything else.
The stars in these different components have different properties, reflecting the different times and conditions of their formation. Halo stars are very old, up to nearly the age of the universe, about 13 billion years. They have very low abundances of heavy elements, because they formed early in the history of the galaxy, when the interstellar medium hadn't yet been enriched by many generations of stellar nucleosynthesis. Bulge stars are also old, though maybe not quite as old as halo stars, and they have a broader range of chemical compositions. Thick disk stars are of intermediate age, perhaps 8 to 12 billion years old. Thin disk stars have a wide range of ages, from newly formed stars all the way up to about 10 billion years. The chemical composition of a star tells you something about when and where it formed. Since the elements heavier than helium are produced in stars, the abundance of these elements in the interstellar medium has been increasing over the history of the galaxy. Old stars, formed early, have low metal content. Young stars, formed recently, have high metal content. This is called the age-metallicity relation, though it's not a simple one-to-one relationship, because of complications like radial mixing, where stars can migrate away from the location where they formed. Different elements are produced by different processes in different types of stars over different timescales. So the relative abundances of different elements in a star are like a fingerprint, encoding information about the population of previous stars whose deaths enriched the material from which the current star formed. For example, elements produced primarily in core collapse supernovae, like oxygen and magnesium, are produced quickly because massive stars have short lifetimes, so they appear early in the galaxy's chemical history. Elements produced primarily in type 1a supernovae, like iron and nickel, take longer to appear because type 1a supernovae involve white dwarfs, which take longer to form. So the ratio of magnesium to iron, or alpha element to iron, tells you about the ratio of core collapse to type 1a supernovae that contributed to the star's material. Old stars, formed when core collapse supernovae dominated, have high alpha to iron ratios. Younger stars, formed after type 1a supernovae, started contributing significantly, have lower alpha to iron ratios. This kind of chemical analysis, called galactic archaeology or galactic chemical evolution, has become a powerful tool for reconstructing the history of the Milky Way. Large spectroscopic surveys like APO-G, GALA, and Gaia-ESO have obtained detailed chemical compositions for hundreds of thousands or millions of stars. And by combining this chemical information with kinematic information from Gaia, which is measuring precise positions, velocities, and distances for over 1 billion stars, we can piece together an increasingly detailed picture of how the Milky Way was assembled. One of the striking discoveries in recent years is evidence that the Milky Way has undergone major merger events with other galaxies. Perhaps the most notable is the so-called Gaia Enceladus, or Gaia sausage event, in which the Milky Way merged with a dwarf galaxy about 8 to 10 billion years ago. The debris from this merger contributes a large fraction of the stars in the inner halo of the Milky Way, and these stars have distinctive chemical and kinematic properties that allow them to be identified. The merger was a major event in the history of our galaxy, and it may have played a role in transforming an early thin disk into what is now the thick disk. There have been other, smaller merger events as well. The Sagittarius dwarf galaxy is currently being torn apart by tidal forces, and its material is being spread through the halo. Various stellar streams have been identified, thin trails of stars from disrupted globular clusters or dwarf galaxies. Each is a witness to the ongoing hierarchical assembly of the Milky Way. Let me shift now to talking about star formation, because I've been discussing what happens after stars form, but not so much how they come to exist in the first place. Stars form in molecular clouds, which are large, cold, dense regions of the interstellar medium composed primarily of molecular hydrogen. Molecular clouds have temperatures of just 10 to 30 degrees above absolute zero and densities of about 100 to 1,000 particles per cubic centimeter. This is still much less dense than air, but it's a lot denser than the average interstellar medium. Molecular clouds have complex filamentary turbulent structures with a wide range of densities and sizes. Within them, there are denser cores, called prestellar cores, which are the immediate precursors of individual stars or small groups of stars. When a prestellar core becomes dense enough for its self-gravity to overcome its internal pressure, thermal, magnetic, and turbulent, it begins to collapse. The collapse is initially isothermal, meaning the temperature stays constant as the density increases, because the gas can efficiently radiate away the heat generated by the collapse. But as the density increases, the gas becomes opaque to its own radiation, and further compression begins to heat it up. A protostar forms in the center of the collapsing core. It's initially small and cool, but it grows rapidly as material continues to fall onto it from the surrounding envelope. Angular momentum is a big issue in star formation. Any small rotation in the initial cloud will be amplified by conservation of angular momentum as the cloud collapses. If nothing removes angular momentum, the collapsing material forms a rapidly spinning disk, and the material can't actually reach the central protostar because it's moving too fast. So most of the material ends up in the disk rather than in the star. In reality, various mechanisms transport angular momentum outward, allowing material to spiral inward through the disk and reach the star. These mechanisms include magnetic torques, viscous friction in the disk, and gravitational torques from disk instabilities. The details are complex and still an active area of research. Some material is also ejected in bipolar outflows and jets that emerge along the rotational axis of the system, carrying angular momentum with them. These jets are among the most striking features of young stellar objects, extending sometimes light years from the source and creating shock features called Herbig-Haro objects, where they collide with the surrounding interstellar medium. While material is still accreting onto the protostar, it's called a Class 0 or Class 1 object, deeply embedded in its dust envelope and observable primarily in infrared and submillimeter wavelengths. As the envelope disperses, the young star becomes visible in optical wavelengths, and it's called a T Tauri star if it's low mass, or a Herbig AE/BE star if it's higher mass. These young stars continue to accrete material from the disk for millions of years, and they're often variable and active, with strong magnetic activity and high X-ray emission. Once the accretion is ended, and the star is settled onto the main sequence, it begins its long, stable life of core hydrogen burning. But the disk material that hasn't been accreted onto the star can go on to form planets. And this is where star formation connects to planet formation and ultimately to the origins of life. Stars don't usually form in isolation. They form in groups from the fragmentation of a single molecular cloud into many prestellar cores. These groups range from small associations of a few dozen stars up to massive clusters containing hundreds of thousands or millions of stars. The clusters that we see today, like the Pleiades or the double cluster in Perseus or the Orion Nebula cluster, are relatively young, and they preserve some information about the process that formed them. Most clusters are not gravitationally bound after their gas is dispersed, and they gradually disperse into the general field of the galaxy. The stars in a cluster all form within a relatively short period, maybe a few million years, from material with similar chemical composition. So the members of a cluster are like siblings, all born together, all with similar starting material. As the cluster disperses, its members go off in their own directions, but they retain their common origin in their chemical signatures. Some clusters remain gravitationally bound for long periods. Open clusters like the Pleiades or Hyades can survive for hundreds of millions of years. Globular clusters, which are much more massive and denser, can survive for the entire age of the universe. The globular clusters we see today orbiting the Milky Way formed very early in the history of the galaxy, or even before the galaxy fully assembled. Some of them may have been the cores of dwarf galaxies that were absorbed into the Milky Way. Globular clusters are fascinating objects in their own right. They're extremely old, with ages typically 11 to 13 billion years. They contain hundreds of thousands to millions of stars, packed into a region only a few tens of parsecs across. The stellar densities in the cores of globular clusters are extraordinary, up to 1 million stars per cubic parsec, compared to about 1 star per cubic parsec in the solar neighborhood. In such dense environments, stellar encounters are common, and unusual objects form. Blue stragglers, for example, are stars that appear younger than their host cluster, and they're thought to form from mergers or mass transfer between binary stars. Also, globular clusters have been used to test our theories of stellar evolution. By fitting the observed distribution of stars in a color magnitude diagram to theoretical models, we can determine the age of the cluster. This provides a lower limit to the age of the universe, since the universe has to be older than the oldest stars. Historically, there was tension between the ages of globular clusters and the age of the universe derived from cosmological measurements. But this tension has been largely resolved with improved measurements, and both give consistent ages around 13 to 14 billion years. Now, let me talk more about stellar rotation and magnetic activity, because these have profound effects on stellar evolution and on the environments of planets around stars. You will love this. Stars are born rotating, inheriting angular momentum from the molecular clouds they formed from. Young stars typically rotate quite rapidly, with rotation periods of a few days or less. As they age, they lose angular momentum through magnetized stellar winds. This process is called magnetic braking, and it's been reasonably well understood for decades. The star's magnetic field, generated by dynamo action driven by convection and rotation, extends into the surrounding space. The wind of charged particles blowing off the star follows the magnetic field lines, and as the star rotates, the field lines drag the wind material with them. This gives the wind a lot of angular momentum, which comes at the expense of the star's rotation. Over time, the star slows down. The rate of spin down depends on the star's rotation rate and its magnetic properties, both of which are themselves connected. Faster rotating stars have stronger dynamos and stronger magnetic fields, which cause more effective spin down. Slower rotating stars have weaker fields and slower spin down. The result is that the rotation rates of stars of a given mass converge over time. This is called gyrochronology, and it can be used to estimate stellar ages from measured rotation periods. The Sun rotates once every 25 days or so at its equator, and the slower at higher latitudes. This differential rotation is one of the key ingredients in the Sun's magnetic dynamo. The interaction of rotation and convection generates the magnetic field, which manifests itself in sunspots, solar flares, coronal mass ejections, and the various other phenomena we lump together as solar activity. The Sun goes through an 11-year activity cycle, during which the number of sunspots varies from a maximum to a minimum and back. The magnetic polarity of the Sun reverses every 11 years, so the full magnetic cycle is 22 years. The underlying cause of the cycle is not fully understood, though it clearly involves the interplay of differential rotation and convection in generating and destroying magnetic flux. Other stars have their own activity cycles, and astroseismology and long-term monitoring have been used to characterize them. Some stars have clear cycles like the Sun, others have less regular activity. Some are in a state of low activity that may be analogous to the Maunder minimum, a period in the 17th century when the Sun had almost no sunspots for several decades. Understanding the range of stellar activity is important for understanding the habitability of planets around other stars. Because activity, especially high-energy emission like flares and coronal mass ejections, can be devastating for planetary atmospheres. Red dwarfs, in particular, are much more active than Sun-like stars, and they remain highly active for much longer periods, potentially billions of years. Since red dwarfs are also the most common type of star, and they have habitable zones close to the star, their activity is a major concern for the habitability of planets around them. Which brings me to the topic of exoplanets and what we've learned about planets around other stars. The first exoplanet around a Sun-like star was discovered in 1995. Since then, thousands more have been discovered using various methods. The transit method, in which a planet passes in front of its star and causes a small dip in the star's brightness, has been the most productive. The Kepler mission alone discovered more than 2,000 confirmed exoplanets and thousands more candidates. The radial velocity method, which detects the wobble of a star caused by the gravitational pull of an orbiting planet, has also been very productive. Direct imaging, gravitational microlensing, and other methods contribute additional discoveries. From this large sample of exoplanets, we've learned a lot. Planets are common, Most sun-like stars have at least one planet, and many have multiple planets. Small planets, roughly Earth-sized to Neptune-sized, are much more common than large ones. Planets exist in a huge range of orbital configurations, including many that are very different from anything in our solar system. Hot Jupiters, which are giant planets in orbits closer than Mercury is to the Sun, were among the first exoplanets discovered, and they were a shock to theorists who had assumed giant planets could only form far from their stars. Now we understand that hot Jupiters likely form far out and migrate inward through interactions with the protoplanetary disk. There are super-Earths and mini-Neptunes, planets larger than Earth but smaller than Neptune, which have no analog in our solar system, but which appear to be extremely common in the galaxy. Their compositions range from mostly rocky to mostly gaseous to mostly water, and there's ongoing debate about how they form and what determines their properties. The habitable zone of a star is the range of orbital distances where a planet with an appropriate atmosphere could have liquid water on its surface. The habitable zone depends on the star's luminosity, and for smaller, cooler stars, it's closer in. Planets in the habitable zones of their stars have been found in significant numbers, though there's not yet definitive evidence that any of them are actually habitable, let alone inhabited. The characterization of exoplanet atmospheres has become possible in recent years, especially with the James Webb Space Telescope. By observing a planet as it transits its star or as it emits its own thermal radiation, we can measure the composition of its atmosphere and detect molecules like water, carbon dioxide, methane, and others. This is an extremely powerful capability, and it's still in its early days. In the coming years, we should be able to characterize the atmospheres of increasingly small and temperate planets, potentially including planets that are similar in size and orbital location to Earth. The search for biosignatures, meaning chemical signatures of life in an atmosphere, is one of the exciting frontiers. The classical biosignature is the simultaneous presence of oxygen and methane, both of which are chemically reactive and shouldn't coexist for long unless something is continuously producing them. On Earth, biology produces both. If we detect a similar combination in another planet's atmosphere, it would be strong, though not conclusive, evidence for life. There are various possible false positives, non-biological processes that could produce similar signatures, and disentangling these is a major challenge. Let me now come back to talking about the endpoints of stellar evolution and go into more depth on white dwarfs, neutron stars, and black holes. White dwarfs are the endpoint of stellar evolution for stars with initial masses less than about 8 solar masses. This includes the vast majority of stars, including the Sun. When such a star finishes its AGB phase, it sheds its outer layers as a planetary nebula, and the exposed core becomes a white dwarf. A typical white dwarf has a mass around 0.6 solar masses packed into a volume roughly the size of Earth. So its density is enormous, about 1,000,000 times the density of water. A teaspoon of white dwarf material would weigh several tons on Earth. White dwarfs are supported by electron degeneracy pressure, as I mentioned before. This pressure has an unusual property. It depends only weakly on temperature, and it depends on density in a way that leads to a strange consequence. More massive white dwarfs are smaller. That's the opposite of what you'd expect from normal objects. If you add mass to a white dwarf, it doesn't get bigger, it gets smaller. This is called the mass-radius relation for white dwarfs, and it was worked out by Subramanian Chandrasekhar in the 1930s. Following the relation, you find that white dwarfs approach zero radius as their mass approaches a critical value of about 1.4 solar masses. This is the Chandrasekhar limit. A white dwarf can't have a mass greater than this. If you tried to add mass beyond the limit, the degeneracy pressure would fail to support it, and it would collapse. Chandrasekhar derived this limit while he was a young graduate student on his ship voyage from India to England to start his studies at Cambridge. He arrived in England, presented his work, and got an unfriendly reception from Arthur Eddington, the leading astrophysicist of the era, who publicly ridiculed Chandrasekhar's conclusion. Eddington believed that some unknown physics must prevent the collapse, and he used his prestige to marginalize Chandrasekhar's work for years. Chandrasekhar was deeply hurt by this and eventually moved to the United States, where he had a distinguished career at the University of Chicago. He was awarded the Nobel Prize in 1983, in part for the work that Eddington had dismissed. The Chandra X-ray Observatory is named after him. When a white dwarf first forms, it's very hot, with surface temperatures of tens or hundreds of thousands of degrees. But it has no source of energy to replace what it radiates away, so it slowly cools over time. Cooling white dwarfs pass through a range of colors, from blue-white to yellow to orange to red, over billions of years. Eventually, in principle, a white dwarf would cool to a black dwarf, a cold, dark object with no significant emission. But the cooling time is so long that no white dwarf in the universe has yet had time to become a black dwarf. The universe isn't old enough. The oldest white dwarfs currently in our galaxy still have surface temperatures of thousands of degrees. The oldest white dwarfs, therefore, provide another lower limit on the age of the universe, or the age of the local region of the galaxy. The coolest, faintest white dwarfs give ages of around 10 to 12 billion years, consistent with the ages derived from globular clusters and from cosmology. White dwarfs have interesting internal structure. As they cool, the ions in their interior arrange themselves into a crystal lattice, starting from the center and working outward. So the core of an old white dwarf is essentially a solid crystal, though a very strange kind of crystal with electrons flowing freely through the ion lattice. This crystallization was predicted theoretically decades ago and has recently been confirmed observationally through subtle features in the cooling curves of white dwarfs. Some white dwarfs are in binary systems where they accrete material from a companion. The accretion can produce various interesting phenomena. If the accreted hydrogen builds up on the surface of the white dwarf and reaches a critical density and temperature, it can ignite in a runaway thermonuclear reaction, producing a nova. Novae are much less energetic than supernovae. They don't destroy the star. They just blow off the accumulated layer, and the process can repeat many times on timescales of decades to millennia. Some novae have been observed to repeat in what are called recurrent novae. If the white dwarf can accumulate mass faster than it loses it, its mass grows toward the Chandrasekhar limit. When it approaches the limit, thermonuclear runaway can happen in the interior, incinerating the star in a Type 1a supernova, as I discussed before. There's ongoing debate about the details of what triggers Type 1a supernovae. The single degenerate scenario involves accretion from a normal star companion. The double degenerate scenario involves the merger of two white dwarfs. Both may occur in different fractions. Neutron stars are the next step in the sequence of stellar remnants. They form from the core collapse of massive stars when the iron core exceeds the Chandrasekhar limit and collapses. The collapse continues until the density reaches nuclear density, at which point the neutrons resist further compression through both neutron degeneracy pressure and the strong nuclear force. A typical neutron star has a mass of about 1.4 solar masses, similar to the Chandrasekhar mass, but its radius is only about 10 to 12 kilometers. Its density is around 10 to the 17th kilograms per cubic meter, comparable to the density of an atomic nucleus. A teaspoon of neutron star material would weigh about 1 billion tons. The gravitational field at the surface of a neutron star is about 200 billion times that at Earth's surface. If you fell onto a neutron star, you'd be flattened into a layer of atoms more or less instantaneously. Neutron stars have complex internal structure. The outer crust is composed of ordinary atoms, though very heavy ones, arranged in a crystal lattice. Deeper down, in the inner crust, the atoms become so squeezed that neutrons drip out of the nuclei and form a superfluid ocean between the ion lattice. Deeper still, in the outer core, the material is a soup of neutrons with a small admixture of protons and electrons. And in the inner core of the most massive neutron stars, the density is so high that we're not entirely sure what the state of matter is. It could be a soup of free quarks. It could involve exotic particles like hyperons or kaon condensates. The equation of state of matter at these densities is one of the outstanding problems in physics. Neutron stars have very strong magnetic fields, typically around 10 to the 12th Gauss. That's about 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have even stronger fields, up to 10 to the 15th Gauss. These extreme fields have all sorts of interesting effects, including quantum electrodynamic effects that make the vacuum around magnetars birefringent, meaning it has different indices of refraction for light polarized in different directions. Magnetars are also responsible for some of the most energetic transient events observed, including so-called giant flares, in which a magnetar releases in a fraction of a second more energy than the sun produces in tens of thousands of years. Many neutron stars are observed as pulsars, meaning they emit beams of radio waves from their magnetic poles, and as the neutron star rotates, the beams sweep around like a lighthouse, and we see periodic pulses if the beam happens to point our way. Pulsars were discovered in 1967 by Jocelyn Bell, a graduate student at Cambridge. She noticed a repeating signal in her radio data, so regular that at first it was jokingly called LGM1 for little green men, since it seemed almost artificial. It was quickly determined that the signal was natural, coming from rapidly rotating neutron stars. The discovery led to a Nobel Prize in 1974, but the prize was given to Bell's advisor, Anthony Hewish, not to Bell herself. This is widely considered one of the great injustices in Nobel Prize history. Bell has been characteristically gracious about it, but the exclusion is often cited as an example of the mistreatment of women in science. Pulsars have periods ranging from milliseconds to seconds. Millisecond pulsars, spinning hundreds of times per second, are thought to be old neutron stars that have been spun up by accretion from a binary companion. The pulses from pulsars are extraordinarily regular, rivaling atomic clocks in stability for the most stable pulsars. This has enabled remarkable tests of fundamental physics. For example, pulsar timing has provided some of the most stringent tests of general relativity. The Hulse-Taylor binary pulsar, discovered in 1974, consists of two neutron stars orbiting each other. As they orbit, they emit gravitational waves, which carry away energy and cause the orbit to slowly decay. The observed decay rate agrees with the predictions of general relativity to better than 0.1%, providing indirect confirmation of gravitational waves decades before they were directly detected. Hulse and Taylor won the Nobel Prize for this work in 1993. More recently, pulsar timing arrays, in which many millisecond pulsars are monitored simultaneously, have been used to search for very low-frequency gravitational waves from supermassive black hole binaries in distant galaxies. Recent results from these arrays have detected a common signal that is consistent with a background of gravitational waves from many such binaries, though confirmation and characterization are ongoing. Neutron stars also come in various other flavors depending on their observational characteristics. There are radio pulsars, as I've discussed. There are X-ray pulsars, which are neutron stars accreting from a binary companion, with the accretion powering strong X-ray emission that gets modulated by the neutron star's rotation. There are magnetars, as I mentioned. There are central compact objects, which are neutron stars and supernova remnants that don't show pulsar activity. There are rotating radio transients, which emit sporadic radio bursts rather than steady pulses. And then there's the newest class of neutron star phenomena, or at least the newest to be understood, the fast radio bursts. Fast radio bursts, or FRBs, are millisecond duration bursts of radio emission that come from cosmological distances. They were discovered in 2007 in archived data from the Parkes Radio Telescope in Australia. For years, their origin was mysterious. Various models were proposed, ranging from magnetars to compact object mergers to more exotic scenarios. Then, in 2020, a fast radio burst was detected from a magnetar in our own galaxy called SGR 1935 plus 2154. This was much closer than any previous FRB, and it was clearly associated with the magnetar. So we now know that at least some FRBs come from magnetars. There may still be multiple mechanisms producing FRBs, though, since the observed properties are quite diverse. Some FRBs repeat, some don't. Some come from young stellar populations, some from old stellar populations. It's likely that there's more than one source, and untangling them is an active area of research. Now let me talk about black holes, which are the third main type of stellar remnant. Black holes are what you get when the collapsing core of a massive star exceeds the maximum mass that can be supported by neutron degeneracy pressure and the strong nuclear force. The exact value of this maximum mass, called the Tolman-Oppenheimer-Volkoff limit, depends on the equation of state of dense nuclear matter, which is not perfectly known. But it's around 2 to 2.5 solar masses. If the collapsing core exceeds this limit, nothing can stop the collapse. The core continues to collapse in principle to zero size and infinite density, forming a singularity. Or at least, that's what general relativity predicts. In reality, quantum gravity effects are expected to take over near the singularity, but we don't have a working theory of quantum gravity, so we don't know what actually happens. What we can describe, using general relativity, is the region outside the collapsing matter. The strong gravity produces an event horizon, a boundary in space-time beyond which no signal can escape to the outside world. Everything inside the event horizon is causally cut off from the outside universe. For a non-rotating black hole, the event horizon is a sphere, and its radius, called the Schwarzschild radius, is proportional to the mass. For a black hole with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. For a black hole with the mass of the Earth, it would be about 9 millimeters. For a supermassive black hole with 1 billion solar masses, it's about 3 billion kilometers, or 20 astronomical units. Black holes have a remarkable property, which is that they're characterized by only a small number of parameters. This is called the no-hair theorem. A black hole, once it settles down from any transient formation event, is described completely by its mass, its angular momentum, and its electric charge. All the other information about what fell into it is, at least classically, lost. This is one of the properties that makes black holes so philosophically challenging. Ordinary matter carries all sorts of information about its history and internal structure. Black holes seem to lose all of that. This connects to the black hole information paradox, which I mentioned when discussing Stephen Hawking earlier. Hawking showed that black holes emit thermal radiation, and if they emit only thermal radiation, they carry no information about what fell in. So information seems to be destroyed, but this violates fundamental principles of quantum mechanics, which requires information to be preserved. The resolution of this paradox has been an active area of research for decades, and there's been significant recent progress based on ideas from string theory and holography, though no complete resolution. Stellar mass black holes have been detected in various ways. The oldest method is through their effects on binary companions. If a black hole is in a binary system with a normal star, the black hole is invisible directly, but it exerts gravitational influence on the star, causing it to orbit an unseen companion. From the orbital motion, we can measure the mass of the invisible object, and if the mass exceeds the maximum mass for a neutron star, it's likely a black hole. Cygnus X1, discovered as an X-ray source in 1964, was the first identified black hole candidate. Additionally, if the black hole is accreting material from the companion star, the accreted material forms an accretion disk that gets extremely hot, emitting X-rays. Many X-ray binary systems contain accreting black holes. From studying these systems, we've learned about the masses of stellar black holes, which typically range from about 5 to 20 solar masses. The direct detection of black holes through gravitational waves has opened a new window in the last decade. In 2015, the LIGO gravitational wave detectors made the first direct detection of gravitational waves, from the merger of two black holes about 1.3 billion light-years away. The signal, called GW150914, was a beautiful chirp of gravitational waves, exactly matching the predictions of general relativity for the inspiral, merger, and ringdown of two black holes. Since then, LIGO and its European counterpart Virgo have detected many more black hole mergers, along with some neutron-star mergers and some mixed neutron-star black hole mergers. The black holes detected through gravitational waves have masses ranging from a few solar masses to about 100 solar masses. Notably, some of them are more massive than the black holes typically inferred from X-ray binaries, and their masses fall in a range that was previously not well populated in our census of black holes. This has taught us about the population of black holes in the universe, and it's raising interesting questions about how such black holes form. Some of them might come from the collapse of very massive stars, but the details of the formation mechanism are still being worked out. There's also the question of intermediate mass black holes, meaning black holes with masses roughly in the range 100 to 100,000 solar masses. These would fill the gap between stellar mass black holes and supermassive black holes. Their existence has been long theorized, but observational evidence has been elusive. Some candidates have been identified in recent years, and gravitational wave observations may eventually detect mergers involving intermediate mass black holes. Supermassive black holes are the largest class, with masses ranging from about 100,000 to 10 billion solar masses. They reside in the centers of most large galaxies, including our own Milky Way. The supermassive black hole at the center of the Milky Way, called Sagittarius, a star, has a mass of about 4 million solar masses. Its existence has been established by observing the orbits of stars near the galactic center, which orbit an unseen massive object with very small size. The observations of these orbits, carried out over decades primarily by two teams led by Reinhard Genzel and Andrea Ghez, provided the most direct evidence for the existence of a supermassive black hole and led to a Nobel Prize in 2020. More recently, the Event Horizon Telescope, a network of radio telescopes across the world operating together as a single virtual telescope, has produced direct images of the immediate surroundings of supermassive black holes. The first such image was released in 2019, showing the black hole at the center of the galaxy M87, with a mass of about 6.5 billion solar masses. The image shows a dark region, the shadow of the black hole, surrounded by a ring of hot glowing material. In 2022, a similar image was released for Sagittarius A star. These images are direct visual confirmation of the existence of supermassive black holes with the properties predicted by general relativity. And they've made supermassive black holes tangible in a way they weren't before. How supermassive black holes formed is one of the outstanding questions in astrophysics. They exist even at very high redshifts, meaning very early in the history of the universe, when there wasn't much time for them to grow through ordinary accretion. Various formation scenarios have been proposed, including direct collapse of massive gas clouds, hierarchical mergers of stellar mass black holes, and rapid accretion in the early universe. But the exact mechanism, or combination of mechanisms, is not settled. Supermassive black holes have a profound influence on their host galaxies. When they accrete material rapidly, they become active. Galactic nuclei, or AGN, which are among the brightest phenomena in the universe. Quasars, which are the most luminous type of AGN, can outshine their entire host galaxy by huge factors and be visible from across the observable universe. AGN emit not just light, but powerful jets of relativistic particles that can extend for hundreds of thousands or millions of light years, well beyond the boundaries of their host galaxies. The energy released by AGN can affect the evolution of the host galaxy through what's called AGN feedback. The radiation and jets from the AGN can heat the gas in the galaxy, prevent it from cooling and forming stars, and even blow it out of the galaxy entirely. This feedback is thought to be important in shaping the properties of galaxies and their central black holes. Indeed, there's a remarkable observed correlation between the mass of a galaxy's central black hole and the properties of the galaxy's bulge, which suggests that the growth of the black hole and the growth of the galaxy are intimately connected. Let me now try to wrap up this very long discussion with some broader reflections on stellar astrophysics and what it teaches us about the universe. Stars are the fundamental building blocks of the visible universe. Almost everything we see in the sky, from the sun and planets to the distant galaxies at the edge of the observable universe, involves stars in some way. Galaxies are collections of stars. Nebulae are the raw material for stars, or the debris of dead stars. Even black holes, though not stars themselves, are typically the remnants of stars. The elements we're made of, the calcium in our bones, the iron in our blood, the oxygen we breathe, were all forged in the interiors of stars or in the explosions that ended their lives. Carl Sagan's famous phrase, that we are made of star stuff, is not a metaphor but a literal biochemical fact. Every heavy element in our bodies has, at some point in the past, been inside a star. It's a remarkable thought. When we look at the stars, we're looking at the factories where the raw materials of our existence were produced billions of years ago in stars long since dead. Star formation continues today and will continue for a long time to come. But the universe is finite, and the rate of star formation has been declining for billions of years, since a peak around 10 billion years ago. The interstellar gas that fuels star formation is gradually being locked up in long-lived stars and remnants that don't return their material to the interstellar medium efficiently. Eventually, in tens of trillions of years, star formation will effectively cease. The stars that exist at that time will burn out one by one over even longer timescales, until the universe is left with only cold, dark remnants, drifting alone in the expanding cosmic void. That's the ultimate fate of the stars in the standard cosmological picture. It's a somewhat melancholy prospect, but it's set against a much longer story of extraordinary creativity, of stars generating the complexity we see around us, and of the emergence of thinking, feeling beings capable of understanding all of this. The universe won't be like this forever, but for now, and for a long time to come, it's a place of profound beauty and richness thanks to the stars. I could keep going, but I think I've probably said more than enough. This has become quite an extensive tour of stellar astrophysics, covering everything from stellar formation and structure to nucleosynthesis, evolution, endpoints, and connections to galaxies, cosmology, and the origin of the elements. If there's something specific you'd like to go deeper on, or a topic I haven't covered that you're curious about, just let me know. Is there a particular thread you'd like to pull on further? For example, we could dive deeper into the physics of specific processes or explore related topics like the interstellar medium, galaxy formation, cosmology, exoplanet atmospheres and habitability, or the search for extraterrestrial life. Or if you're interested in the history of astronomy and the scientists who developed our current understanding, we could go in that direction. Or into ongoing research and open questions. Just let me know what you'd like to continue with. All right, let me continue by exploring some topics I haven't yet covered in depth, and by going deeper into some of the frontier research areas in stellar astrophysics. Let me start with the interstellar medium, since I've mentioned it repeatedly but haven't described it in detail. The interstellar medium, or ISM, is the material that fills the space between stars in a galaxy. It's not a vacuum, though it's much less dense than any vacuum we can create on Earth, and it's a highly complex multi-phase system that plays a central role in the ecology of galaxies. The ISM contains gas, dust, cosmic rays, magnetic fields, and radiation, all interacting in complicated ways. The gas is mostly hydrogen and helium, with small amounts of heavier elements, reflecting the composition of the material returned to the ISM by dying stars. The dust is composed of small solid particles, typically less than a micron in size, made of silicates carbon compounds, and ices. Dust makes up about 1% of the mass of the ISM by mass, but it plays a role out of proportion to its abundance by absorbing and re-emitting starlight, catalyzing chemical reactions on its surface, and shielding molecules from destructive ultraviolet radiation. The gas in the ISM exists in several different phases, characterized by different temperatures and densities. The hot ionized medium has temperatures of millions of degrees and very low densities, created by supernova shock waves that heat the gas as they expand. The warm ionized medium has temperatures of about 10,000 degrees, and it's ionized by ultraviolet radiation from hot stars. The warm neutral medium has similar temperatures but is neutral, not ionized. The cold neutral medium has temperatures of tens to hundreds of degrees and higher densities. And the molecular medium, where star formation occurs, has temperatures of just 10 to 30 degrees and much higher densities. These different phases are in rough pressure equilibrium with each other. Hot phases have low density and high temperature. Cold phases have high density and low temperature. The product of pressure times temperature is roughly constant across the phases. This equilibrium is maintained by heating and cooling processes that balance each other. Heating comes from photoionization by ultraviolet radiation, cosmic rays, and shock waves from supernovae. Cooling comes from radiation, primarily line emission from atoms, ions, and molecules. The molecular medium is particularly interesting because it's where stars form. Molecular clouds are cold and dense, and they're the sites of a rich chemistry. Astronomers have detected over 300 different molecules in interstellar space, ranging from simple diatomic molecules like carbon monoxide and molecular hydrogen to complex organic molecules like methanol, ethanol, and even amino acid precursors. The chemistry in molecular clouds occurs both in the gas phase and on the surfaces of dust grains, where reactions can occur that are slow or impossible in the gas phase. The organic chemistry of interstellar space is remarkable, and it suggests that the raw materials for life may be widespread in the universe, delivered to planetary systems as they form from collapsing molecular clouds. Cosmic rays are high-energy charged particles that pervade the galaxy. They're accelerated to enormous energies by supernova shock waves and other processes. Cosmic rays play important roles in the ionization of molecular clouds, in heating the ISM, and in driving chemistry. They're also important for the origin of life, potentially, since they contribute to the mutation rate of DNA, though they can also be destructive to complex molecules and to organisms. Magnetic fields permeate the ISM. The typical field strength is only a few microgauss, which is extremely weak by everyday standards, but the fields extend over such large volumes that they play significant roles. They influence the dynamics of the ISM. They help to support molecular clouds against gravitational collapse. They channel the flow of cosmic rays, and they generate synchrotron radiation from cosmic ray electrons that can be observed at radio wavelengths. The interplay of all these components in the ISM produces the beautiful and complex structures we see in images of nebulae. The Orion Nebula, for example, is a rich star-forming region where young stars are illuminating the surrounding gas, creating an emission nebula. The Horsehead Nebula is a dark cloud silhouetted against a brighter background, an example of the cold molecular medium. The Crab Nebula is the expanding remnant of a supernova, still glowing from the energy input of the pulsar at its center. Now, let me talk about some of the frontier topics in stellar astrophysics that are being actively researched right now. One area of intense activity is the study of stellar mergers. When two stars in a binary system come into contact, they can merge into a single, more massive star. These mergers are rare, but they produce distinctive observational signatures, and they're thought to be responsible for various classes of stars that don't fit into standard stellar evolution scenarios. Blue stragglers in globular clusters, as I mentioned, are one example. Some peculiar stars, called Thorne-Zeitkopf objects, are hypothesized to form from the merger of a neutron star with a red giant, though no definitive example has been identified. A related and even more exciting area is the study of compact object mergers, meaning the mergers of neutron stars and black holes. These events produce gravitational waves that can be detected by LIGO and Virgo, and in the case of neutron star mergers, they also produce electromagnetic radiation across the spectrum. The first detection of a neutron star merger, GW170817, in August 2017, was a landmark event in astronomy. Gravitational waves from the inspiral were detected by LIGO and Virgo, followed by a burst of gamma rays a couple of seconds later, and then a rich electromagnetic afterglow observed by dozens of telescopes across the world. The event confirmed that neutron star mergers are the source of at least some short gamma ray bursts, and it provided direct evidence that heavy elements like gold, platinum, and the lanthanides are produced in neutron star mergers through the rapid neutron capture process. This is one of the outstanding questions in nucleosynthesis, and the detection of GW170817 substantially resolved it. The R process, or rapid neutron capture process, is one of the ways that elements heavier than iron are produced in the universe. In the R process, atomic nuclei rapidly capture many neutrons, one after another, before there's time for the resulting neutron-rich nuclei to decay. This produces very neutron-rich isotopes, which then decay through beta decay to produce stable heavy nuclei. About half of the elements heavier than iron are produced this way, including many familiar elements like iodine, xenon, gold, platinum, and uranium. Where the R process happens has been debated for decades. The two main candidates are core collapse supernovae and neutron star mergers. The detection of the kilonova associated with GW170817 provided direct spectroscopic evidence for R-process nucleosynthesis in the ejected material, confirming that neutron star mergers are at least one important site of the R process. Another frontier area is the study of black hole formation and demographics. As I mentioned, the black holes detected through gravitational waves have masses that don't perfectly match what was expected from standard stellar evolution scenarios. There are questions about the so-called mass gap, which is a range of masses between about 45 and 130 solar masses, where black hole formation from single stars is thought to be suppressed by pair instability. But black holes in this mass range have been detected. How they formed is an open question. They may have formed through mergers of smaller black holes, or through mergers of stars in dense clusters, or through some other channel. There's also the question of the mass gap between neutron stars and black holes. The maximum mass of a neutron star is thought to be around 2 to 2.5 solar masses, and the minimum mass of a black hole from single-star evolution is thought to be around 5 solar masses. So there's a gap between 2.5 and 5 solar masses where compact objects seem to be rare. But some detections have found objects in this mass range, suggesting that either the gap isn't as clean as thought, or there are mechanisms to produce compact objects in this range that we don't fully understand. Another frontier is the study of the first stars, called population 3 stars. These are the very first generation of stars formed from primordial gas that contained only hydrogen and helium with no heavier elements. Because they had no metals to help cool the gas and fragment it, they're thought to have been very different from later stars, possibly extremely massive, hundreds or even thousands of solar masses. They would have had short lives, ending in either core collapse supernovae, or, if massive enough, in direct collapse too. Black holes, potentially seeding the supermassive black holes we see today. Population 3 stars have never been directly observed. They're all long gone, having died in the first few 100 million years after the Big Bang. But we look for their signatures in various ways. One way is by searching for very metal-poor stars in the Milky Way, which are thought to have formed from material enriched by just a few population 3 supernovae. Some of these stars have been found with extraordinarily low metal content, less than 1 part in 100,000 of the Sun's metal content. Their chemical patterns give us clues about the properties of the population 3 stars whose deaths enriched their material. Another way to search for population 3 stars is through observations of the very early universe. The James Webb Space Telescope has been pushing back the frontier, observing galaxies at redshifts of 10 and higher, meaning we're seeing them as they were less than 500 million years after the Big Bang. Some of these very early galaxies may still contain population 3 stars, or at least their immediate descendants. Detecting the signatures of population 3 stars in these galaxies is one of the goals of ongoing observations. There have been intriguing hints, but no definitive detection yet. Another area of active research is understanding stellar mass loss, particularly for massive stars. Massive stars lose a substantial fraction of their initial mass over their lifetimes through stellar winds and eruptive mass loss events. The rate and mechanism of mass loss profoundly affects the star's evolution and its ultimate fate. But mass loss is difficult to measure and to model, and there are significant uncertainties. One particularly striking type of mass loss is seen in luminous blue variables, or LBVs. These are extremely massive luminous stars that undergo periodic eruptions in which they eject solar masses of material in a short time. The most famous example is Eta Carinae in the southern hemisphere, which underwent a great eruption in the 1840s, becoming for a time the second brightest star in the sky, and ejecting about 10 solar masses of material that we can now see as an expanding nebula around the star. Eta Carinae is one of the most massive stars known, with a current mass of around 100 solar masses. It will eventually explode as a supernova, though we don't know exactly when. It could be tomorrow, or it could be tens of thousands of years from now. When it does explode, it will be a spectacular event, and it will teach us a lot about the deaths of very massive stars. Now let me talk about some big-picture cosmological questions that connect to stellar astrophysics. One is the question of dark matter. Dark matter is a form of matter that doesn't emit or absorb electromagnetic radiation, but which reveals itself through its gravitational effects. It's about 5 times more abundant than ordinary matter in the universe, and it dominates the gravitational potential of galaxies and clusters of galaxies. But what dark matter actually is remains unknown. It's one of the biggest mysteries in physics and astronomy. Stellar astrophysics connects to dark matter in several ways. Stars trace the gravitational potential of their host galaxy, so by measuring the motions of stars, we can measure the distribution of dark matter. This has been done in various ways, including studies of the rotation curves of spiral galaxies, the velocity dispersions of stars in elliptical galaxies and dwarf galaxies, and the tidal streams from disrupted globular clusters and dwarf galaxies. All these measurements point to the existence of large amounts of dark matter surrounding galaxies in extended halos. There have also been attempts to explain dark matter as being composed of astrophysical objects like faint stars, brown dwarfs, or black holes. These candidates were called MACOs, for massive compact halo objects. Various searches have been conducted, mostly using gravitational microlensing, to detect the effects of MACOs on the light from background stars. These searches have found some MACOs, but not enough to account for the observed dark matter. So dark matter appears to be something more exotic than ordinary astrophysical objects. The leading candidates for dark matter are various types of hypothetical particles, particularly weakly interacting massive particles, or WIMPs, and axions. Direct detection experiments have been searching for these particles for decades, with steadily improving sensitivity, but no confirmed detection. The nature of dark matter remains one of the great unsolved problems. Another cosmological question that connects to stellar astrophysics is the Hubble tension. The Hubble constant, which measures the current expansion rate of the universe, can be determined in 2 different ways. One way is from measurements of the cosmic microwave background, the radiation left over from the Big Bang, combined with our cosmological model. The other way is from measurements of standard candles in the nearby universe, like Cepheid variable stars and Type 1. A supernovae, which give us distances to nearby galaxies that we can combine with redshifts to measure the expansion rate. These two methods give different values, which don't agree within their quoted uncertainties. The tension has been around for several years, and it's been getting more statistically significant as measurements improve. It's one of the most important puzzles in cosmology right now. There are various proposed resolutions, including new physics that modifies the cosmological model, or systematic errors in one or both methods. Stellar astrophysics is central to the local measurements, particularly the calibration of the Cepheid distance scale, which is one of the key steps in the local determination of the Hubble constant. Yet, another frontier is multi-messenger astronomy, which is the combined observation of astronomical events across multiple channels, including electromagnetic radiation, gravitational waves, neutrinos, and cosmic rays. The neutron star merger GW 170817 was a landmark event for multi-messenger astronomy, with detections in gravitational waves and across the electromagnetic spectrum. Since then, other multi-messenger events have been observed, including neutrinos from active galactic nuclei and from a tidal disruption event in which a star was torn apart by a supermassive black hole. Neutrinos, which are nearly massless particles that interact very weakly, are extremely difficult to detect, but they carry unique information because they can escape from the interiors of dense objects that block electromagnetic radiation. Neutrinos from the Sun have been detected for decades, and they've been crucial for understanding the interior of the Sun. Neutrinos from supernova 1987A were detected in a burst of just a few seconds, providing the first observation of neutrinos from a supernova and confirming the basic picture of core collapse supernovae as neutrino-driven explosions. We're now able to detect high-energy neutrinos from cosmic sources thanks to the IceCube Neutrino Observatory at the South Pole. IceCube consists of a cubic kilometer of ice instrumented with thousands of detectors, which can detect the faint flashes of light produced when high-energy neutrinos interact in the ice. IceCube has detected neutrinos from various astrophysical sources, and it's opening up a new window on the high-energy universe. Looking to the future, there are many exciting projects and missions coming online in the next decade that will advance our understanding of stellar astrophysics. Let me mention a few. The Vera Rubin Observatory, formerly called the Large Synoptic Survey Telescope, or LSST, is a new ground-based telescope in Chile that will begin operations soon. It will survey the entire southern sky every few nights for 10 years, producing an unprecedented data set for time-domain astronomy. It will discover millions of transient events, including supernovae, tidal disruption events, and variable stars. It will map the Milky Way in exquisite detail, discovering new stellar streams and faint dwarf galaxies. It will also produce a massive catalog of asteroids and other solar system objects. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will have a wide field of view and will survey large areas of the sky in infrared wavelengths. It will study dark energy, discover thousands of exoplanets through microlensing, and characterize the properties of stars and galaxies. It's essentially a Hubble-sized telescope, but with a field of view 100 times larger. The extremely large telescope, being built in Chile, will have a 39-meter mirror when it's completed, dwarfing current ground-based telescopes. It will be able to directly image exoplanets around nearby stars, characterize their atmospheres, resolve the surfaces of nearby stars, and probe the composition of the earliest galaxies. Future gravitational wave detectors, including the space-based LISA mission and next-generation ground-based detectors like Cosmic Explorer and Einstein Telescope, will greatly expand the range of gravitational wave sources we can observe. LISA will detect gravitational waves from massive black hole mergers throughout the universe. Next-generation ground-based detectors will observe stellar mass compact object mergers with much higher sensitivity, potentially detecting nearly every such merger in the observable universe. New neutrino observatories, including upgrades to IceCube and completely new detectors, will further expand our capabilities in neutrino astronomy. And missions like the Habitable Worlds Observatory, being planned for the 2040s, will directly image Earth-like exoplanets around nearby stars and characterize their atmospheres in detail, searching for signs of life. The future of stellar astrophysics and of astronomy in general is extraordinarily bright. We're going to learn things in the coming decades that will fundamentally change our understanding of the universe and our place in it. Let me now turn to some more speculative topics. At the intersection of astrophysics with philosophy and with broader questions about our place in the cosmos. One question that comes up naturally when discussing stars and habitability is the Fermi paradox. The paradox is named after Enrico Fermi, who reportedly asked over lunch with colleagues, "Where is everybody?" The question refers to the apparent contradiction between the high probability that intelligent civilizations should exist elsewhere in the galaxy, given the vast number of stars and planets, and the lack of any evidence for such civilizations. The Milky Way contains hundreds of billions of stars, and most of them have planets. Even if only a tiny fraction of planets are habitable, and only a tiny fraction of habitable planets develop life, and only a tiny fraction of planets with life develop intelligence, there should still be many intelligent civilizations in the galaxy. And even if only a small fraction of those civilizations were to develop technology and expand into the galaxy, they should have colonized the entire galaxy by now in just a few tens of millions of years, which is a blink of an eye compared to the age of the galaxy. So why don't we see any evidence of them? There are various proposed resolutions to the Fermi paradox. One possibility is that life is much rarer than we think, and we're actually alone, or nearly alone, in the galaxy. Perhaps the origin of life is extremely improbable, requiring conditions that occur only very rarely. Perhaps the emergence of intelligence or of technological civilization is even more improbable. This is called the rare Earth hypothesis, and it argues that Earth is special and we're likely alone. Another possibility is that civilizations are common, but don't last long. Perhaps they typically destroy themselves through war, environmental collapse, or other means before they can expand into the galaxy. This is called the Great Filter hypothesis, and it has an ominous implication. If the Great Filter is behind us, we've already passed the crucial test and we're likely to survive. But if the filter is ahead of us, we may be facing an existential challenge that we haven't yet reckoned with. Yet another possibility is that civilizations exist but don't expand, either because interstellar travel is prohibitively difficult, because they choose not to expand for reasons we don't understand. Perhaps they exist in forms we don't recognize, or communicate in ways we can't detect, or deliberately hide from us. Or perhaps we're simply looking in the wrong way, or not for long enough. We've only been able to detect radio signals for about a century, and we've only been actively searching for signals for a few decades. It's possible that other civilizations exist, but we just haven't found them yet. The Fermi paradox is one of those questions where we don't have enough data to know the answer. But as our capabilities improve, particularly in the detection and characterization of exoplanet atmospheres, we should be able to make progress on some aspects of the question. In particular, If we find biosignatures on multiple exoplanets in the coming decades, that would suggest life is common. If we find biosignatures on none of the planets we can characterize, that would push toward the idea that life is rarer than we hoped. Another topic worth touching on is the anthropic principle and the question of why the universe has the properties it does. The properties of stars and of everything else in the universe depend on the values of various fundamental physical constants: the strength of gravity, the strength of the electromagnetic force, the masses of the fundamental particles, and various other quantities determine what's possible in the universe. And many of these quantities appear to be fine-tuned for the existence of complex structures like stars, planets, and living organisms. For example, if the strength of the strong nuclear force were slightly different, either the diproton would be bound, in which case all the hydrogen would have fused to helium in the early universe, and there would be no long-lived stars, or the deuteron would be unbound, in which case nuclear fusion in stars would be very difficult. Either way, the universe would be very different, and probably wouldn't support complex chemistry or life. Similarly, if the cosmological constant, which drives the accelerating expansion of the universe, were much larger, structures like galaxies wouldn't form. If the initial density fluctuations in the early universe were much smaller, structures also wouldn't form. There are many such examples where the parameters of the universe appear to be balanced on a knife edge for the existence of complex structures. Various responses to this apparent fine-tuning have been proposed. One is that the fine-tuning is an illusion, and there are physical reasons why the parameters have the values they do that we haven't yet discovered. Another is that the fine-tuning reflects the operation of some kind of teleological or design principle in the universe. Another is the multiverse hypothesis, which posits that our universe is one of many, with different parameters in different universes, and we naturally find ourselves in one where the parameters allow our existence. This is called the anthropic principle. The anthropic principle has been controversial in physics. Some see it as a legitimate scientific hypothesis with observable consequences. Others see it as an evasion, a way of avoiding the search for deeper explanations. The truth is probably somewhere in between, and the answer likely depends on the specific fine-tuning being considered. The multiverse itself is a controversial concept, and there are various versions of it in different physical theories. In cosmology, eternal inflation predicts an infinite multiverse in which our observable universe is one of many bubbles. In string theory, there are supposedly around 10 to the 500 possible vacua, corresponding to different possible universes with different physical parameters. In quantum mechanics, the many worlds interpretation posits that every quantum measurement creates parallel universes for each possible outcome. These are very different concepts, and the extent to which any of them corresponds to physical reality is debated. Whether or not the multiverse is real, our universe is undeniably one that supports rich structure and complexity, and stars are central to that structure. Without stars, there wouldn't be planets, wouldn't be heavy elements, wouldn't be complex chemistry, wouldn't be life, wouldn't be us. Stars are the fundamental drivers of complexity in the universe. Let me also touch on the topic of the far future of the universe, which is a natural extension of thinking about the endpoints of stellar evolution. The universe is currently in a phase of accelerating expansion driven by dark energy. If dark energy continues behaving as it currently does, the expansion will accelerate forever and the universe will get progressively emptier as galaxies recede from each other faster than the speed of light. Distant galaxies will eventually cross our cosmic event horizon and become fundamentally unreachable and unobservable. Within a galaxy like the Milky Way, star formation will gradually decline as the gas supply is depleted, New stars will stop forming eventually, and the existing stars will burn out one by one over trillions of years. The longest-lived stars, red dwarfs, can shine for trillions of years, so the final generations of stars in a galaxy will burn out over a period of about 100 trillion years. After that, the galaxy will be dark, populated only by the remnants of stars, white dwarfs, neutron stars, and black holes. The white dwarfs will slowly cool over timescales much longer than the current age of the universe, eventually becoming black dwarfs, cold and inert. Neutron stars will similarly cool. Black holes will slowly evaporate through Hawking radiation, though this takes so long that even stellar mass black holes take about 10 to the 67 years to evaporate, and supermassive black holes take up to 10 to the 100 years. This is such an unimaginably long time that ordinary language struggles to convey it. Eventually, over these enormous timescales, even matter itself may not be stable. Various theories predict that protons will eventually decay, though the timescale is at least 10 to the 34 years and probably much longer. If protons do decay, all ordinary matter in the universe will eventually decompose into elementary particles. The very far future of the universe, then, may be a state called heat death, in which the universe is filled with a thin, cold soup of elementary particles and radiation, with no significant structure and no useful energy for any process to occur. This is a dark and lonely fate for the universe, but it's what the standard cosmological model predicts if current trends continue for an unimaginably long time. Of course, there are many uncertainties in the far future of the universe. Dark energy could change its behavior. New physics could reveal that the future is quite different from what we currently predict. But based on our best current understanding, the universe will continue to expand and cool until it reaches a state of maximum entropy and minimum activity. It's a somewhat bleak prospect, but it's set against a much longer story of extraordinary richness and beauty in the current era of the universe. The universe is currently in something like a golden age, with structures at all scales, from atoms to galaxies to clusters, all interacting in complex ways. Stars are shining, planets are forming, life is evolving, at least on our planet and possibly on many others, and thinking beings like ourselves are trying to understand the universe we find ourselves in. This state of affairs is temporary, in cosmic terms, but it's what makes the universe interesting and meaningful, at least from our perspective. Let me shift gears now and talk about some of the historical development of stellar astrophysics, since I've been focused mostly on the science itself rather than on how we came to understand it. The scientific study of stars really began with the invention of the telescope in the early 1600s. Before then, stars were known only as points of light in the sky, and their nature was largely mysterious. The ancient Greeks had various theories about what stars were, ranging from holes in a celestial sphere through which we could see a distant fire, to eternal, unchanging divine beings. Aristotle's cosmology, which dominated European thought for nearly 2 millennia, held that the celestial realm was fundamentally different from the terrestrial realm, made of a fifth element called quintessence, and was eternal and unchanging. The invention of the telescope shattered this view. Galileo, using one of the first astronomical telescopes, discovered that the Milky Way is composed of countless stars, that Jupiter has moons, that Venus has phases, and that the Sun has spots. These discoveries showed that the heavens were not perfect and unchanging, and they helped to establish the Copernican view that the Earth is a planet orbiting the Sun, not the center of the universe. Over the following centuries, telescopes improved, and astronomers cataloged more and more stars, measured their positions with increasing precision, and began to understand their motions. The heliocentric model was solidified, and the vast scale of the universe began to be appreciated. But the actual nature of stars remained largely mysterious. They were understood to be similar to our sun, but at enormous distances. But their internal structure, their energy source, and their evolution were unknown. A key development came in the 1830s and 1840s, when astronomers first successfully measured the distances to nearby stars using parallax. The parallax method uses the apparent shift in a star's position as the Earth moves around the Sun, which allows the distance to be calculated using simple geometry. The first successful parallax measurements were made by Friedrich Bessel, who measured the distance to the star 61 Cygni in 1838, and by other astronomers who measured other nearby stars around the same time. These measurements confirmed that stars are extraordinarily far away, and they allowed the first calculations of stellar luminosities. Another key development was the invention of spectroscopy in the mid-1800s. When light from a star is passed through a prism or diffraction grating, it's dispersed into its component wavelengths, producing a spectrum. The spectrum contains dark lines, called absorption lines, at specific wavelengths where certain elements absorb light. By identifying these lines with the elements that produce them, astronomers could determine the chemical composition of stars. This was a revolutionary discovery. Before spectroscopy, it seemed impossible that we could ever know what stars are made of, since they were so far away. The philosopher Auguste Comte, in 1835, famously listed the composition of the stars as an example of knowledge that would be forever beyond our reach. Just a few decades later, spectroscopy proved him wrong. Spectroscopy revealed that stars are made of the same elements as those on Earth, though in different proportions and at different temperatures and pressures. This was a profound discovery, showing that the same physical laws and the same materials operate throughout the universe. The observation of helium in the sun's spectrum in 1868, before helium was known on Earth, was a striking demonstration of the power of spectroscopy. Helium was actually discovered in the sun before it was discovered on Earth. In the late 1800s and early 1900s, astronomers began to classify stars based on their spectra. Different stars have different spectra, reflecting different temperatures, compositions, and other properties. The classification scheme that eventually became standard is the OBAFGKM sequence, which I mentioned earlier. This classification was developed at Harvard College Observatory, largely by a team of women astronomers led by Edward Pickering, including Annie Jump Cannon, Henrietta Swan Leavitt, Antonia Mori, and Williamina Fleming. These women, often called the Harvard computers, made enormous contributions to astronomy, though their work was often underappreciated at the time. Cannon personally classified hundreds of thousands of stellar spectra, developing the classification scheme that's still used today. Leavitt discovered the period luminosity relation for Cepheid variables, which became the foundation for measuring cosmic distances. The next major step was the development of the Hertzsprung-Russell diagram in the early 1900s. Einar Hertzsprung and Henry Norris Russell independently plotted stars according to their luminosity and their temperature or spectral type, and discovered the pattern I described earlier. Most stars fall on the main sequence, with smaller populations of giants, supergiants, and white dwarfs. This diagram became a fundamental tool for understanding stellar evolution. The next great step was understanding what powers stars. In the 1800s, various theories had been proposed for the source of the sun's energy, including chemical combustion, gravitational contraction, and meteoric infall. But none of these could account for the sun's enormous energy output over the billions of years that geology suggested for the age of the Earth. This was a major puzzle. Lord Kelvin, one of the leading physicists of the 19th century, calculated that gravitational contraction could power the sun for only about 30 million years, which was much less than the age required by geology and biology. This led to significant tension between physicists and geologists, which was only resolved in the early 1900s with the discovery of radioactivity, which revealed a new form of energy that could power the Earth's interior, and eventually with the understanding of nuclear fusion, which explained the sun's energy source. The idea that nuclear reactions might power stars was proposed by Arthur Eddington in the 1920s, based on Einstein's mass-energy equivalence and on the observation that 4 hydrogen atoms weigh slightly more than 1 helium atom. The difference in mass, if it could somehow be converted to energy, would be enormous. Eddington couldn't yet explain the mechanism, but he argued that stars must be powered by some form of nuclear reaction converting hydrogen to helium. The mechanism was worked out in the 1930s, primarily by Hans Bethe and others, who identified the proton-proton chain and the CNO cycle as the fusion mechanisms in stars. Bethe won the Nobel Prize in 1967 for this work, and his understanding of stellar energy generation was one of the great intellectual achievements of the 20th century. The theory of stellar structure was developed by many physicists and astronomers over the first half of the 20th century, including Eddington, Chandrasekhar, Martin Schwarzschild, and others. The equations of stellar structure, which describe how properties like temperature, pressure, and density vary through a star, were formulated, and methods were developed for solving them numerically. This allowed astronomers to construct detailed models of stars and to predict their evolution over time. The theory of stellar evolution was worked out in the mid-1900s, particularly by Fred Hoyle and his collaborators. Hoyle also contributed to nucleosynthesis theory in the famous B2FH paper of 1957, which laid out the theory of how the elements are produced in stars. Hoyle was a fascinating character, brilliant but often unconventional in his views. He never won the Nobel Prize, partly because of controversies about his role in various discoveries, and partly because he held unconventional views on some topics, including his lifelong opposition to the Big Bang Theory, which he actually named, somewhat mockingly, in a 1949 radio broadcast. The theory of stellar collapse in compact objects was developed in the mid-1900s, with contributions from Robert Oppenheimer and others in the 1930s and 1940s, and further work in the 1960s and beyond, particularly after the discovery of pulsars in 1967, confirmed the existence of neutron stars. Black holes were more controversial for longer, but they became increasingly accepted through the 1960s and 1970s as observational evidence accumulated and as theoretical work by Kip Thorne, Roger Penrose, Stephen Hawking, and others clarified their properties. Cosmology and the Big Bang model were developed largely in parallel with stellar astrophysics, and the two fields have become deeply intertwined. The Big Bang was proposed by Georges Lemaitre in the 1920s, and it was confirmed by various observations over the following decades, most notably the discovery of the cosmic microwave background in 1964. The abundance of light elements produced in the Big Bang, which I mentioned earlier, was one of the key predictions that was confirmed by observations, showing that the Big Bang model was correct. The story of stellar astrophysics is one of remarkable progress over the last few centuries, from complete ignorance about the nature of stars to a detailed understanding of their structure, evolution, and role in the universe. And the progress continues today, with new observations and new theoretical work constantly refining our understanding. Let me now touch on some topics I haven't yet covered, or covered only briefly. One is the physics of stellar atmospheres, which is where we actually see the light of a star. The interior of a star is opaque, so we can't directly observe it. What we see is the atmosphere, which is the outermost layer where the star transitions from opaque to transparent. Light from deeper layers is absorbed and re-emitted many times before it escapes, but the light that finally leaves the star comes from the atmosphere. The physics of stellar atmospheres is quite complex. The atmosphere is not in perfect thermodynamic equilibrium because there's a net flow of radiation outward. The temperature varies with depth, and different wavelengths of light are formed at different depths. This produces the absorption lines we see in stellar spectra, which are formed by atoms and ions in the atmosphere absorbing light at specific wavelengths. Epic. By modeling the physics of stellar atmospheres in detail and comparing the models to observed spectra, we can extract information about the stars. We can determine their temperature, their surface gravity, their chemical composition, their rotation rate, their magnetic field strength, and various other properties. This is one of the main ways we learn about individual stars. Stellar atmosphere modeling is one of those areas where the physics gets quite deep, involving radiative transfer, atomic physics, plasma physics, and computational techniques. There are various codes that have been developed over the years for calculating stellar atmosphere models. Comparing these models to high-resolution spectra of stars is one of the standard tools for stellar analysis. For the Sun, we can do much more detailed observations because it's so close. We can resolve features on its surface, we can measure its rotation, and we can even, through helioseismology, probe its interior. Helioseismology uses the observation of oscillations on the surface of the Sun to infer properties of the interior. The Sun has millions of different modes of oscillation, and by measuring the frequencies of these modes, we can constrain the structure of the interior. This has provided strong tests of solar models and has revealed details of the Sun's interior that would otherwise be impossible to observe. Similar techniques have been applied to other stars in a field called astroseismology. Stellar oscillations can be measured through very precise photometry, looking for small variations in a star's brightness that correspond to the oscillations. The Kepler Space Telescope, which was designed primarily to search for exoplanets by detecting transits, also produced a wealth of astroseismology data, allowing astronomers to constrain the interior structures of many stars. This has been particularly valuable for evolved stars like red giants, where different modes of oscillation probe different depths in the star. Another topic is stellar magnetic fields, which I've mentioned a few times but haven't discussed in depth. Stars have magnetic fields generated by dynamo action in their interiors. The Sun has a complex magnetic field that varies over an 11-year cycle, going from a period of low activity called solar minimum to a period of high activity called solar maximum, and back. During solar maximum, there are many sunspots, which are regions of strong magnetic field on the surface, and the Sun produces frequent flares and coronal mass ejections. During solar minimum, there are few sunspots, and the Sun is quieter. Other stars have magnetic activity that varies with time in similar ways, though the specifics vary from star to star. Some stars have much stronger fields than the Sun, and some have weaker fields. Young stars are typically more magnetically active than older stars because they rotate faster, which drives a stronger dynamo. As stars age and lose angular momentum through their winds, they spin down and become less active. This age-activity rotation relation is one of the ways we can estimate the ages of stars in a technique called gyrochronology. Magnetic activity has important effects on stars and their planets. Flares from active stars can strip the atmospheres of nearby planets, potentially making them uninhabitable. This is a Particular concern for planets around red dwarf stars, which tend to be more active than sun-like stars and to remain active for longer periods. Red dwarfs are otherwise attractive targets for the search for habitable planets because they're the most common type of star and their habitable zones are close in, making planets easier to detect. But their activity may pose challenges for habitability. Yet another topic is the influence of stars on the interstellar medium beyond their immediate vicinity. Stars produce enormous amounts of energy over their lifetimes, and much of that energy is deposited in the surrounding interstellar medium through radiation, winds, and supernova explosions. This energy input, called stellar feedback, has profound effects on galactic evolution. Stellar feedback regulates star formation. When a young star cluster forms, the young massive stars quickly ionize the surrounding gas, produce winds and radiation pressure, and eventually explode as supernovae. All of this energy input disrupts the parent molecular cloud, preventing further star formation and eventually dispersing the gas back into the interstellar medium. This is one of the reasons that star formation is inefficient. Only a small fraction of the gas in a molecular cloud actually gets converted to stars before the cloud is disrupted. Stellar feedback also drives galactic winds, which are outflows of gas from galaxies. When enough supernovae explode in a galaxy in a short time, they can drive a wind that carries gas out of the galaxy, sometimes even out of the galaxy's dark matter halo. This can quench star formation in the galaxy, at least temporarily, and it can also enrich the intergalactic medium with heavy elements. Galactic winds are one of the main mechanisms by which heavy elements are distributed on cosmological scales. Understanding stellar feedback in detail is one of the challenges of galaxy formation theory. The processes involved span an enormous range of scales, from the sub-parsec scales of individual star formation to the megaparsec scales of galactic winds and their impact on the intergalactic medium. Simulating these processes requires sophisticated numerical techniques and careful modeling of the underlying physics. Now, let me talk about some specific stars that are particularly famous or interesting to make some of this discussion more concrete. Betelgeuse, in the constellation Orion, is one of the most famous stars in the sky. It's a red supergiant, one of the largest stars visible to the naked eye. If Betelgeuse were placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter, possibly out to Saturn. It's about 700 times the diameter of the Sun. It has a mass of about 15 to 20 solar masses, which means it's destined to explode as a core collapse supernova at some point in the future. The exact timing is uncertain, but it's probably within the next 100,000 years or so. Incredible. Betelgeuse gained particular attention in late 2019 and early 2020, when it dimmed dramatically to about a third of its normal brightness. There was speculation that it might be about to explode. In fact, the dimming was caused by a combination of a large amount of dust being ejected from the star, blocking some of its light, and a natural drop in the star's brightness due to its pulsation. Betelgeuse is a variable star with brightness that varies on multiple timescales due to its complex convective envelope. The dimming episode showed that stars can behave in unexpected ways, and it gave astronomers a great opportunity to study Betelgeuse in detail. When Betelgeuse does eventually explode, it will be a spectacular event. The supernova will be visible in the daytime sky, possibly as bright as a full moon at peak. It will last for months and gradually fade. It will not, however, be dangerous to Earth. At its distance of about 550 light-years, it's far enough that the radiation would not significantly affect our planet. The neutrinos from the explosion would be detected by our neutrino detectors and might even give us a warning a few hours before the visible explosion. since neutrinos escape from the collapsing core immediately, while the visible light only appears when the shock wave breaks out of the star's surface. Sirius, the brightest star in the night sky, is another famous star. It's a binary system consisting of a main sequence A-type star called Sirius A and a white dwarf called Sirius B. Sirius A is about twice the mass of the Sun and about 25 times more luminous. Sirius B is one of the closest known white dwarfs, and it was one of the first white dwarfs to be identified. The system is close, only 8.6 light-years away. Sirius has interesting historical and mythological connections. The ancient Egyptians used the heliacal rising of Sirius when it first became visible above the horizon in the pre-dawn sky to mark the beginning of their year and to predict the annual flooding of the Nile. Sirius is also central to the mythology of various cultures. There's an interesting historical puzzle involving Sirius. Some ancient sources, particularly the Roman poet Cicero and the astronomer Ptolemy, described Sirius as red, while today it appears blue-white. This has led to speculation that Sirius B, before it became a white dwarf, might have been a red giant that dominated the light of the system. But the timescales don't quite work out. Sirius B is thought to have become a white dwarf about 120 million years ago, long before human history. So the red descriptions are probably due to other factors, like atmospheric effects or errors in the sources. Polaris, the North Star, is famous for its position near the North Celestial Pole, which makes it appear nearly stationary while other stars rotate around it. It's not actually a particularly bright star, ranking around 50th in the sky, but its position makes it very useful for navigation. Polaris is actually a triple star system, consisting of a Cepheid variable and two smaller companions. As a Cepheid, its brightness varies with a period of about 4 days, though the variation is small. Alpha Centauri is the closest star system to the Sun at a distance of about 4.37 light-years. It's actually a triple system consisting of two Sun-like stars, Alpha Centauri A and B, that orbit each other closely, and a distant red dwarf companion called Proxima Centauri. Proxima is the closest individual star to the Sun at 4.24 light-years. Proxima is known to host at least one planet in its habitable zone, called Proxima Centauri b, which was discovered in 2016. This planet is the closest known potentially habitable exoplanet, though its actual habitability is uncertain due to concerns about the stellar activity of Proxima. Wow! Barnard's star is another nearby red dwarf at a distance of about 6 light-years. It's notable for having the highest proper motion of any known star, meaning it appears to move across the sky faster than any other star. It's moving toward the Sun and will be closest in about 10,000 years at a distance of about 3.75 light-years, temporarily making it closer than Proxima Centauri is now. Tabby's star, also known as KIC 8462852, is a somewhat mysterious star that has attracted significant attention. It shows unusual dimming events, sometimes dropping in brightness by up to 20%, in irregular patterns that don't match the signatures of typical variable stars or transiting planets. Various explanations have been proposed, including uneven rings of dust, comet fragments, or even, speculatively, some kind of alien megastructure. The most likely explanation, based on more detailed observations, is uneven dust in the vicinity of the star, though the details remain uncertain. Tabby's star is a reminder that there are still surprises out there, even for well-studied stars. Let me now turn to some cutting-edge research topics that I've mentioned briefly, but want to explore in more detail. One is the field of stellar streams and Milky Way archaeology. When a small satellite galaxy or globular cluster is torn apart by the tidal forces of the Milky Way, its stars form long streams that trace the past trajectory of the disrupted object. These streams contain valuable information about the history of the Milky Way and about the distribution of dark matter in its halo. The Sagittarius stream is one of the most prominent examples. The Sagittarius dwarf galaxy is currently being torn apart by the Milky Way, and its stars are spread over long trails that wrap around the sky. By tracing these streams and modeling their dynamics, astronomers can learn about the mass distribution of the Milky Way, including the distribution of dark matter. Many other streams have been discovered in the Milky Way's halo, some of them very faint and only detectable through careful searches of stellar catalogs. The Gaia satellite has been transformative for this field, providing precise measurements of the positions and motions of billions of stars, which allow astronomers to identify streams as groups of stars with similar motions. This is a rapidly developing field, and we're building up a detailed picture of the history of the Milky Way through the discovery and analysis of these streams. The Milky Way has grown over its history by absorbing smaller galaxies. The stellar populations of the halo of the Milky Way contain the debris of these past mergers. By identifying groups of stars with similar chemical compositions and orbital properties, astronomers can identify individual accretion events in the Milky Way's past. The largest such event was called Gaia Enceladus, or the sausage, which occurred about 10 billion years ago and contributed a substantial fraction of the stars in the Milky Way's inner halo. This event was identified only recently, thanks to Gaia data, and it has significantly refined our picture of the Milky Way's formation. Another cutting-edge area is the study of chemical evolution in the Milky Way, using large spectroscopic surveys. Surveys like APOG, GALA, and Gaia ESO have measured the detailed chemical compositions of hundreds of thousands to millions of stars. By analyzing the abundances of many different elements in each star, astronomers can piece together the history of chemical enrichment in the Milky Way. Different elements are produced in different types of stars and by different processes. For example, alpha elements like oxygen, magnesium, and silicon are produced primarily in core collapse supernovae, which happen relatively quickly after star formation. Iron peak elements are produced in significant amounts by type 1a supernovae, which take longer to occur since they involve white dwarf accretion or mergers. So the ratio of alpha elements to iron in a star tells us something about when the star formed and about the mix of supernovae that enrich the gas it formed from. By analyzing these patterns for large samples of stars, astronomers have identified different populations in the Milky Way with different formation histories. There's a thin disk population with certain chemical characteristics, and a thick disk population with different characteristics that formed earlier. There are halo stars with very low metallicities that formed in the earliest stages of the galaxy or were accreted from small dwarf galaxies. This chemical archaeology, combined with the dynamical information from Gaia, is giving us an increasingly detailed picture of how the Milky Way formed and evolved. Another area is the search for exoplanets and the characterization of their atmospheres, which I've mentioned but want to expand on. Over 5,000 exoplanets have been discovered as of the mid-2020s, and the number keeps growing. Most of these were discovered by transit surveys like Kepler and TESS, which detect the small dip in a star's brightness when a planet passes in front of it. Others were discovered by radial velocity surveys, which detect the small motion of a star induced by the gravitational pull of an orbiting planet. Others have been discovered by direct imaging, microlensing, or other techniques. Amazing. The population of exoplanets we've discovered is enormously diverse. There are hot Jupiters, gas giants orbiting extremely close to their stars, with temperatures of thousands of degrees. There are super-Earths and mini-Neptunes, planets larger than Earth but smaller than Neptune, which don't have analogs in our solar system but are very common around other stars. There are planets in the habitable zones of their stars, which have the right temperature to potentially have liquid water. There are planets in binary star systems, some of them orbiting around both stars, like the fictional Tatooine. The transit method also allows us to characterize the atmospheres of some exoplanets through a technique called transmission spectroscopy. When a planet transits its star, some of the star's light passes through the planet's atmosphere before reaching us. By analyzing the spectrum of the transmitted light, we can identify absorption features from gases in the atmosphere, telling us what the atmosphere is made of. The James Webb Space Telescope has been particularly powerful for exoplanet atmosphere studies. It has detected water vapor, carbon dioxide, methane, and other molecules in the atmospheres of various exoplanets. It has characterized the atmospheres of hot Jupiters in unprecedented detail. And it's starting to make progress on characterizing the atmospheres of smaller, potentially habitable planets, though these are more challenging because the signal is much weaker. The ultimate goal of exoplanet atmosphere studies is to detect biosignatures, meaning gases or combinations of gases that would indicate the presence of life. The classic biosignature is the combination of oxygen and methane in an atmosphere, because these two gases react with each other and shouldn't coexist without a continuous source, which on Earth is provided by life. Other biosignatures include specific patterns of gases that would be hard to produce abiotically. Detecting biosignatures on an exoplanet would be one of the most profound discoveries in the history of science, potentially confirming that we're not alone in the universe. But we're not there yet. Current instruments can characterize atmospheres of hot, close-in planets, but detecting biosignatures on a rocky, temperate planet around a sun-like star is beyond current capabilities. This will require next-generation observatories, including the Habitable Worlds Observatory that I mentioned earlier, which is being planned for the 2040s. Even before that, upcoming instruments and telescopes will make significant progress. Let me also discuss the intersection of stellar astrophysics with astrobiology, which is the study of the origin, evolution, distribution, and future of life in the universe. Astrobiology draws on many different fields, including biology, chemistry, geology, planetary science, and astronomy. Stellar astrophysics contributes to astrobiology in several ways. It tells us about the stars around which life might exist and about the conditions those stars provide for their planets. It tells us about the timescales available for the evolution of life around different types of stars, and it tells us about the ultimate origins of the elements that make up living organisms. Every element in our bodies, other than hydrogen and helium, was produced in a star. The carbon in our cells was made in the cores of red giants through the triple alpha process. The oxygen we breathe was made in massive stars through advanced burning stages. The iron in our blood was made in type 1a supernovae, or in the cores of massive stars in their final moments. The calcium in our bones was made in massive stars and supernovae. The nitrogen in our DNA was made in the CNO cycle in stars. We are, quite literally, made of star stuff, as Carl Sagan famously said. This connection between stars and life is one of the most profound aspects of modern science. It means that life is not separate from the cosmos, but deeply embedded in its history and its material. The atoms in our bodies have their own long stories, having been forged in stars that lived and died billions of years ago, then dispersed into space, then incorporated into the gas cloud that formed our solar system, then integrated into the biosphere of Earth, and then eventually into us. And when we die, our atoms will continue on their journeys, being recycled into other living organisms, eventually ejected from the solar system perhaps, and possibly incorporated into other stars and other worlds in the far future. This perspective connects us to the cosmos in a very direct way. We're not just observers of the universe, we're participants in its ongoing story. We're one of the ways that the universe organizes matter and energy into complex structures, and through our understanding, we're one of the ways the universe becomes aware of its